Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated ideas are allowed to take their time, and the universe can be explored without anyone expecting you to take notes. Tonight, we're going to look at something that seems simple from a distance, but becomes much more interesting the closer we get to it: the different kinds of star systems that exist across the universe. When most of us picture a star system, we probably imagine something rather familiar. There is one star in the middle, a collection of planets moving around it, perhaps a few moons, some asteroids, a comet passing through every now and then, and at least one planet whose inhabitants spend an unreasonable amount of time wondering what is happening everywhere else. That description works quite well for our own solar system. The Sun sits at the centre, containing almost all of the system's mass, while 8 planets and a large population of smaller objects travel around it. It is the arrangement we know best, so it is easy to assume that nature probably uses roughly the same design elsewhere. But the universe has never shown much interest in keeping things that simple. Many stars are not alone. Some travel through space with a second star permanently attached to their lives by gravity. Others belong to groups of 3, 4, 5 or even more stars, all following complicated orbits around shared centres of mass. Some stars are surrounded by planets. Others appear to have no planets at all. Some planetary systems contain worlds packed so closely together that several of their orbits could fit inside the orbit of Mercury. Others have giant planets circling so far from their stars that a single year might take centuries. There are young systems surrounded by thick disks of gas and dust, still assembling planets from leftover material. There are old systems whose stars have already changed dramatically, leaving behind white dwarfs, neutron stars or black holes. There are systems where 2 stars orbit peacefully at comfortable distances, and others where one star pulls material away from its companion so aggressively that the pair produces powerful X-rays, explosions or both. Apparently even stars can have complicated relationships. Over the course of this journey, we're going to sort through these different arrangements carefully. We'll begin with the simplest systems and gradually work towards some of the strangest. We will look at stars that live alone, stars that come in pairs, crowded stellar families, planetary systems around several suns, newborn stars that have barely begun shining, and systems containing the compact remains of stars that reach the ends of their normal lives. And before we head out among all of those distant suns, I'd like to ask you something. Where are you listening from tonight? Perhaps you're somewhere with a clear sky outside your window. Maybe you're in a city where only the brightest stars can compete with streetlights. Perhaps you're near the coast, somewhere rural, high in a building, tucked into bed, sitting on a sofa, or listening through headphones while the rest of the house has gone quiet. And if you happen to know, what is the brightest star you can see from where you live? You certainly don't need to go outside and check. This is science for sleep, not science for putting on shoes at midnight. You can simply think about the last clear night you remember. That small point of light probably looked completely isolated. Almost every star does when viewed with the unaided eye. The distances between stars are enormous, and even stars that are physically connected to one another can appear to us as a single point. That leads to one of the first useful things to understand about star systems. What we see from Earth is not always what is actually there. For thousands of years, people looked at the night sky and naturally assumed that most stars were individual objects. A bright dot looked like one star because, well, it looked like one star. There wasn't much reason to suspect otherwise. Telescopes changed that. Once astronomers gained enough magnifying power and enough precision, some apparently ordinary stars separated into pairs. Later, improved instruments revealed systems containing 3 stars or more. Modern spectroscopy made the situation even more surprising, because astronomers discovered stars that looked completely single through a telescope but revealed, through changes in their light, that an unseen companion was orbiting them. In some cases, 2 stars are so close together that even powerful telescopes cannot easily separate them. Astronomers can still detect the partnership because each star moves toward us and away from us as the pair orbits. That motion shifts features in the star's spectra slightly toward the blue or the red. In other words, the stars may look like one object, but their light quietly admits that there are two of them. This matters because multiple star systems are not unusual accidents. They are a major part of the stellar population. The exact fraction depends on the kind of stars you're talking about. Low-mass red dwarfs are more commonly found alone, while massive stars are much more likely to have stellar companions. Sun-like stars fall somewhere between those extremes. As astronomers survey different populations, the general picture is clear. Nature produces both solitary stars and groups of stars, and the balance changes depending on stellar mass and formation conditions. That means our Sun is neither the universal standard nor some strange exception. It belongs to one of several common arrangements, and there is another distinction worth making before we go farther. A star system is not necessarily the same thing as a planetary system. A star system refers broadly to one or more gravitationally connected stars and the objects associated with them. A planetary system usually refers specifically to planets and smaller bodies orbiting a star or group of stars. Our solar system is both. The Sun is the star. Earth, Jupiter, Saturn, the other planets, dwarf planets, moons, asteroids, comets, dust, and countless smaller objects make up the surrounding planetary system. But imagine two stars orbiting one another with no known planets. That is still a star system. Imagine one star with 5 planets. That is a star system and a planetary system. Imagine 3 stars in a gravitational hierarchy, with one planet orbiting one member of the trio. Again, you have both. Astronomy is full of terms that sound perfectly straightforward until someone asks you to define them precisely. Then everyone quietly reaches for a diagram. The word system itself is useful because gravity naturally creates organization. Stars do not simply sit still in empty space. They move, they orbit, they interact with nearby objects. Their gravity shapes the paths of planets, smaller stars, gas, dust, asteroids, and anything else close enough to become involved. At the scale of a galaxy, all of those systems are moving as well. Our Sun travels around the centre of the Milky Way at hundreds of thousands of kilometres per hour. One complete orbit takes roughly a couple of 100 million years. The last time the solar system was in approximately the same place in its galactic orbit, dinosaurs were living on Earth. They were not, as far as we know, keeping track. Within that enormous galactic motion, the planets continue circling the Sun. The Moon circles Earth. Asteroids follow their own paths. Comets move along highly stretched orbits. The Sun itself responds slightly to the gravitational pulls of the planets, especially massive Jupiter. Nothing is truly sitting at a perfectly fixed centre. Even when we say that a planet orbits a star, both objects technically orbit their shared centre of mass, known as the barycenter. If one object is vastly heavier than the other, that point usually lies inside the larger object, so describing the planet as orbiting the star is perfectly practical. With 2 stars of more similar mass, however, the shared centre can lie in empty space between them. Both stars then make obvious loops around that common point. This simple rule is behind an extraordinary variety of systems. Change the masses of the stars and the orbits change. Move them closer together and their gravitational interaction becomes stronger. Give one star a planet and that planet must navigate the gravitational influence of everything nearby. Add a 3rd star and the mathematics becomes more complicated. Add several planets to the arrangement and the system starts looking less like a simple classroom diagram and more like something that would make a computer very happy and a person with a pencil slightly nervous. Gravity, however, manages perfectly well. One reason astronomers care so much about star system types is that the arrangement of stars can affect almost everything that happens afterward. It can influence whether planets form. It can change where those planets are able to maintain stable orbits. It can alter the evolution of the stars themselves. In close binary systems, one star can eventually expand and transfer material to its companion. That process may change both stars dramatically. Under the right circumstances, it can contribute to novae, supernovae, X-ray sources, neutron star mergers, and other energetic events. A companion star can turn an otherwise ordinary stellar life into something much more eventful. Multiple stars can also disturb disks of planet-forming material. Their gravity may carve gaps, tilt disks, truncate them, or move planets into unusual orbits. Yet planets clearly can survive in surprisingly complex environments. Astronomers have discovered worlds orbiting one star in a binary, while another star circles farther away. They have also found circumbinary planets, worlds that orbit around two stars at once. If you've ever watched science fiction and thought that a planet with two sunsets seemed like a suspiciously convenient bit of scenery, nature would like a word. Such planets are real. Their skies would behave differently from ours, of course. Depending on the star's positions and the planet's orbit, there could be two distinct suns moving across the sky. Sometimes they might appear close together. At other times they could separate more widely. One could eclipse the other. Sunrise and sunset patterns could become far more complicated than the simple routine we experience on Earth. And two stars are only the beginning. Triple star systems can be arranged in several ways, although stable systems usually develop some sort of hierarchy. Often two stars form a relatively close binary, while a third star travels around the pair at a much greater distance. That separation is important. Three stars of similar mass placed at similar distances from one another can produce chaotic orbital behavior. Gravity is predictable in principle, but systems with three interacting bodies can become extremely sensitive to their starting conditions. Nature tends to favor arrangements that can survive. A close pair with a distant third companion is much more stable than three stars continually passing close to one another, like people trying to use the same revolving door. Larger stellar systems usually follow similar patterns. Groups of 4 or more stars can contain binaries orbiting binaries, or several nested levels of stellar companions. The architecture can become surprisingly elaborate. Then we have systems that challenge the ordinary meaning of the word star. A white dwarf, for example, is the hot, dense remnant left behind after a star similar to the Sun exhausts its fuel and sheds its outer layers. It no longer produces energy through ordinary hydrogen fusion in its core, yet it can remain part of a stellar system. A neutron star is even more extreme. It can contain more mass than the Sun compressed into an object only around the size of a city. And a black hole may be the final remnant of a much more massive star. Put one of these objects beside an ordinary star and you get an entirely different type of system. Sometimes the compact object quietly orbits its companion. Sometimes it pulls material away. Gas falling toward a neutron star or black hole can become extremely hot and release intense X-rays. This allows astronomers to find compact objects that would otherwise be difficult or impossible to see directly. In those systems, an invisible object can reveal itself by what it does to its neighbour. Then there are stars that have only recently formed. Stars are born inside cold clouds of gas and dust. Regions within those clouds collapse under gravity, creating dense protostars surrounded by disks of material. Those disks can eventually produce planets, moons, asteroids, and comets. But stars rarely form in complete isolation. Many are born in groups or clusters, which means nearby stars can interact while their planetary systems are still taking shape. Some stars remain gravitationally bound to companions. Others are separated by encounters and eventually travel through the galaxy alone. So when we ask what kinds of star systems exist, we're also asking how stars are born, how they remain together, how they separate, how planets fit into the arrangement, and how all of those relationships change over billions of years. A system that begins with two ordinary stars may not remain that way. One star may age first because it began with more mass. It can swell into a giant while its companion remains relatively unchanged. Material may pass from one star to the other. Eventually one might become a white dwarf while the second continues shining normally. Much later, the second star may evolve too. A binary can therefore pass through several very different identities without ever ceasing to be the same gravitational partnership. The same is true of planetary systems. Young planets can migrate, orbits can change, worlds can collide or be ejected, stars can lose mass as they age, causing surviving planets to move into wider orbits. Some planets may even survive the death of their stars. Astronomers have found evidence of planetary material around white dwarfs, and planets have been detected around pulsars, a type of rapidly rotating neutron star. That last example is particularly strange. A neutron star is the collapsed remnant of a star that exploded. It is difficult to imagine a less welcoming beginning for a planetary neighbourhood, yet planets exist around some of them. The first confirmed planets discovered outside our solar system were, in fact, found orbiting a pulsar rather than a normal sun-like star. The universe has a talent for answering simple questions in inconvenient ways. Ask, what does a planetary system look like? And it provides a planet orbiting the remains of an exploded star. Ask, how many suns can a world have? And it provides planets in multiple star systems. Ask, are stars usually alone? And the answer becomes, that depends on what kind of star you mean. This is why it helps to move through the possibilities one at a time. We don't need to memorize a complicated classification chart. We can simply begin with the most straightforward arrangement and let the complexity build naturally. There will be familiar systems and unusual ones. There will be stars separated by enormous distances and stars orbiting so closely that they distort one another. We'll encounter systems that remain calm for billions of years, and systems where material is constantly moving from one object to another. We'll also keep one question in mind throughout the journey: how normal is our own solar system? It is tempting to imagine that astronomy has already answered that. After all, thousands of exoplanets have been confirmed, and astronomers now know about an extraordinary variety of planetary arrangements. Yet the more systems we discover, the more obvious it becomes that the galaxy does not follow one standard blueprint. Some systems contain hot Jupiters, giant planets orbiting extremely close to their stars. Some contain several rocky worlds packed into small regions. Some have planets on noticeably eccentric or tilted orbits. Some orbit small red dwarfs. Some belong to binary stars, and some resemble our own system in certain ways while differing sharply in others. We are still learning where the solar system fits within that enormous range. That is part of what makes star systems such a useful way to explore astronomy. They connect many different subjects at once: gravity, stellar evolution, planet formation, orbital mechanics, supernovae, black holes, habitability, and the long history of galaxies. A star is never only a glowing point. Its mass tells us how it will live. Its companions can change how it evolves. Its planets can preserve clues about how it formed. Its motion can reveal unseen objects. Its eventual remains can continue influencing a system long after the star has stopped shining in the ordinary way. And from Earth, most of this is happening at distances so enormous that even the nearest star beyond the Sun is more than 4 light-years away. That means the light reaching us tonight began its journey years ago. For more distant systems, the delay can be hundreds, thousands, or millions of years. Astronomers therefore never observe the universe exactly as it is at this instant. They observe information that has travelled across space before arriving at telescopes. Fortunately, stars are not known for changing their plans because someone is running late. For the kinds of systems we'll be discussing, that delay usually gives us a perfectly useful view of how nature organises stars and planets. If you're enjoying the slower pace of this exploration, and you'd like to support Science for Sleep, you can give the video a like or subscribe to the channel. It helps more people find these long, quiet science journeys, including those who enjoy learning before sleep, and those who begin with every intention of listening to the whole thing before discovering, somewhere around minute 37, that morning has arrived. And if you do fall asleep, that's perfectly fine. The stars have been doing this for billions of years. They'll manage without us for the evening. For now, we only need somewhere simple to begin, before we visit double suns, triple systems, planets moving around multiple stars, newborn stellar groups, and the compact remains of dead stars. It makes sense to start with the arrangement closest to our everyday intuition. One star. These solitary suns may sound like the least complicated members of the stellar population. The difficulty begins with a surprisingly basic question. What does it actually mean for a star to be alone? From our point of view, the answer seems obvious. If we look through a telescope and see one star, then there is one star. Unfortunately, astronomy has spent several centuries demonstrating that the universe is not obligated to make things obvious. A star can appear completely solitary and still have a faint companion hiding nearby. The companion may be too dim to see, too close to separate from the brighter star, or so far away that confirming whether the two objects are genuinely bound by gravity takes years of careful measurement. An unseen companion could even be a white dwarf, neutron star, or another object that contributes very little visible light. So when astronomers describe a star as single, what they usually mean is that no gravitationally bound stellar companion is known. That qualification matters. It leaves room for better telescopes, longer observations, and the possibility that nature has placed something inconveniently faint exactly where it is hardest to detect. Our own sun is the most familiar example. The sun is a single star. It has planets, dwarf planets, moons, asteroids, comets, dust, and enough smaller objects to keep astronomers busy indefinitely. But it has no known stellar companion. This occasionally disappoints people, because stories about a hidden second sun have been around for a long time. At various points, ideas have appeared suggesting that the sun might possess a distant companion sometimes called Nemesis, perhaps responsible for periodically disturbing comets and sending them toward the inner solar system. It is a wonderfully dramatic name for something that has never been found. Modern surveys have placed strong limits on the possibility of an undiscovered nearby stellar companion to the sun. There is no evidence of a second star quietly following us through the galaxy at the edge of the solar system, which is probably just as well. One sun already handles the lighting. The sun is officially designated in rather less exciting ways than many distant stars because it is our local star and did not need to be discovered in a telescope survey. Astronomers simply call it the Sun, or Sol in some contexts. It is a G-type main sequence star, roughly 4.6 billion years old, containing more than 99% of the mass of the solar system. Its singleness has had important consequences for the environment around it. Because there is no nearby second star repeatedly disturbing the planets, the solar system has been able to maintain a comparatively straightforward architecture. The planets move around one dominant central mass. Their orbits certainly influence one another, and Jupiter in particular is massive enough to produce noticeable gravitational effects, but there is no second sun constantly tugging on the system from another direction. That does not mean single-star systems are automatically calm. Planets can scatter one another. Giant planets can migrate. Smaller bodies can be thrown out completely. Even a system with one star can produce enough gravitational drama to fill a respectable television series. But the absence of another star removes one major source of complication. Single stars also give astronomers some of the cleanest places to study planet formation. The basic idea begins inside a collapsing cloud of gas and dust. As part of the cloud falls inward under gravity, conservation of angular momentum causes the material to flatten into a rotating disk around the forming star. Most of the material ends up in the star itself. The remainder can form planets. If only one star forms at the centre, the surrounding disk can extend outward without having a nearby stellar companion carving through it, truncating it, or pulling material away. That does not guarantee planets will form, but it gives the disk a relatively uncomplicated gravitational environment in which to work. Our own solar system appears to have begun this way about 4.6 billion years ago. The young sun was surrounded by a protoplanetary disk containing gas, dust, ice, and heavier elements produced by earlier generations of stars. Tiny grains collided and stuck together. Larger structures grew, planetesimals formed. Some eventually became planetary embryos. After millions of years of collisions, accretion, migration, and a great deal of orbital rearrangement, the recognizable solar system emerged. The result was not inevitable. Another disk around another solitary star might produce a completely different collection of planets. That becomes obvious when we look beyond the Sun. One of the nearest and most famous apparently single stars is Barnard's star, also catalogued as GJ 699 and HIP 87937. It lies only about 6 light-years away and is a small red dwarf. Its catalogue names may sound slightly less charming than Barnard's star, but they are useful because astronomical catalogues contain enormous numbers of objects, and relying entirely on memorable names would become difficult very quickly. Barnard's star is named after the American astronomer Edward Emerson Barnard, who measured its remarkable motion across the sky in the early 20th century. It has the highest known proper motion of any star. Proper motion is not the speed of the star directly toward or away from us. It is the apparent movement of the star sideways across the background sky. Most stars are so distant that their positions seem almost fixed over a human lifetime. Barnard's star is close enough, and moving quickly enough relative to us, that its position changes noticeably when measured across years. If you could watch the night sky for thousands of years with the patience of a mountain, you would see Barnard's star gradually shifting against the more distant stellar background. Fortunately, astronomers invented photography, so nobody has to volunteer. Barnard's star is very different from the Sun. It is a red dwarf, much smaller, cooler, and dimmer than our star. Red dwarfs are the most common type of star in the Milky Way. They burn their hydrogen extraordinarily slowly, which means they can remain on the main sequence for far longer than stars like the Sun. The smallest red dwarfs can theoretically continue shining for trillions of years. That is much longer than the current age of the universe, so no low-mass red dwarf has yet had enough time to complete its normal main sequence life. Every such star that ever formed and survived is still somewhere in the earlier stages of its existence. There is something almost unfairly efficient about that. The Sun receives roughly 10 billion years of ordinary hydrogen-burning life and has already used nearly half of it. A small red dwarf looks at that schedule and apparently decides not to rush. Barnard's star is especially interesting because it shows that a single star system does not need to resemble ours in order to be considered one of the same broad type. Its central object is still one star. Any planets or smaller bodies associated with it orbit that one stellar mass. The scale, temperature, radiation environment, and possible planetary conditions can all be very different, but the basic architecture remains straightforward. There is no known second star sharing control of the system. A little farther away, another useful example gives us something closer to the Sun. Tau Ceti is a nearby star in the constellation Cetus. It appears in several astronomical catalogues as HD 10700, HIP 8102, and GJ 71. It is a G-type star, slightly smaller and cooler than the Sun, and for decades it has attracted attention because it is one of our relatively nearby Sun-like stellar neighbours. If the name Tau Ceti sounds familiar even if you do not spend your evening studying star catalogues, science fiction may be responsible. Nearby Sun-like stars have always been irresistible locations for imaginary civilizations. They are close enough to feel almost reachable, at least by astronomical standards, and similar enough to the Sun that writers can reasonably wonder what kinds of worlds might exist around them. The universe, unfortunately, uses a slightly different definition of close. Tau Ceti is almost 12 light-years away. Light from the star takes nearly 12 years to reach us, despite travelling at approximately 300,000 kilometers per second. If someone around Tau Ceti had an extraordinarily powerful telescope and happened to be looking toward Earth tonight, they would not see Earth as it is tonight. They would see Earth as it was almost 12 years ago, The same delay applies in reverse. The Tau Ceti we observe is Tau Ceti from nearly 12 years in our past. That is still practically next door compared with most of the Milky Way. Tau Ceti is especially useful in thinking about single-star systems because it demonstrates that having one star does not mean having nothing else. Observations have revealed a substantial debris disk around Tau Ceti. A debris disk consists of dust and small material left behind after the main era of planet formation. Collisions among asteroids, comets, and other small bodies can continually replenish the dust. Our solar system has related populations of material in the asteroid belt and Kuiper belt, although an observer looking at another system from many light years away might describe its structure differently depending on what their instruments could detect. The presence of debris around Tau Ceti gives astronomers information about what happened during and after the formation of the system. Planets may be extraordinarily difficult to see directly, but dust can reveal that something has been happening there for a very long time. This is one of the useful tricks of studying star systems. Astronomers often cannot see every important object. Instead, they look for consequences. A star moves slightly because a planet pulls on it. Its light dims because something passes in front. A disk contains gaps or concentrations that may have been shaped by gravitational interactions. An atmosphere absorbs particular wavelengths. A star system rarely hands us a complete inventory. It leaves evidence. Another nearby solitary star takes that idea even further. Epsilon Eridani, catalogued as HD 22049, HIP 16537, and GJ 144, lies roughly 10.5 light-years from Earth. It is a K-type star, somewhat smaller and cooler than the Sun, and it is younger than our own system. Simbad lists the catalogue identifiers HD 22049 and HIP 16537, while NASA observations have studied both its debris material and a giant planet associated with the system. Epsilon Eridani is especially interesting because it gives astronomers something resembling a younger version of the sort of environment our solar system once possessed. The star is surrounded by debris. A giant planet, Epsilon Eridani b, has been studied orbiting it. The architecture is not simply a miniature copy of the solar system, but that is precisely why it is useful. Astronomers do not expect other systems to repeat our history perfectly. They compare them. A younger nearby star with a planet and substantial leftover material can show us processes that are difficult to reconstruct around the older Sun, because much of the original evidence has already been removed, incorporated into planets, or scattered. Looking at Epsilon Eridani is a little like visiting a construction site after living for years in a finished house. You begin noticing where the beams came from. Of course, the comparison has limits. Epsilon Eridani is cooler than the Sun. Its planet follows its own orbit. Its debris structure is its own. Its history involved conditions we cannot simply assume were identical to ours. Still, it shows how much variety can exist within the category of single-star systems. The Sun, Barnard's star, Tau Ceti, and Epsilon Eridani are all solitary stars in the sense that no confirmed stellar companion dominates their local architecture. Yet place them side by side, and they hardly look like copies. The Sun is a middle-aged G-type star with 8 major planets. Barnard's star is a much smaller red dwarf. Tau Ceti is another relatively Sun-like star accompanied by substantial debris. Epsilon Eridani is a younger K-type star with a well-studied debris environment and a giant planet. One star at the centre does not tell you what the rest of the system will look like. It only tells you where the gravitational organisation begins. And even that simple statement comes with complications. Consider the word centre. In diagrams of the solar system, the Sun is usually placed exactly in the middle, while the planets move around it. That is good enough for most purposes, but technically the Sun also moves. Every object with mass pulls on every other object with mass. Jupiter pulls on the Sun, Saturn pulls on the Sun, Earth pulls on the Sun. You pull on the Sun as well, although the Sun has so far declined to comment. The entire solar system moves around a shared centre of mass. Because the Sun is enormously more massive than any planet, that centre is usually close to the Sun and often inside it. But Jupiter is massive enough that the Sun's position shifts noticeably as the two objects orbit their common barycenter. Astronomers use this same principle to detect planets around other stars. Imagine a distant star with a large planet. We may not be able to see the planet directly because it is faint and lost in the glare of its star. But the planet's gravity causes the star to move in a small orbit around their shared barycenter. From Earth, that motion can produce changes in the star's spectrum. When the star moves slightly toward us, its spectral lines shift toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This is the radial velocity method, and it has been enormously important in the search for exoplanets. A planet may be invisible, but gravity is careless about keeping secrets. The transit method works differently. If a planet's orbit happens to line up correctly from our viewpoint, the planet passes across the face of its star. The star becomes slightly dimmer. Then the planet moves on, and the brightness returns to normal. If the dip repeats at regular intervals, astronomers can infer that an orbiting object is passing in front. The amount of dimming helps estimate the planet's size. Combine transit measurements with other methods, and a surprising amount of information can emerge from what initially looks like a tiny change in a distant point of light. Single stars are particularly useful targets for these techniques, because the light usually comes from one dominant stellar source. In binary systems, the situation can become harder to interpret. Two stars may contribute light. One star can eclipse the other. Both can move significantly. A planet may orbit one star or both. The resulting signals can still be understood, but the bookkeeping becomes more demanding. Around a single star, the basic question is often simpler. What is pulling on this star, or what is passing in front of it? That simplicity has made solitary stars especially attractive in the search for potentially habitable planets. Habitability, however, requires some caution. The phrase habitable zone is often used to describe the range of distances around a star where a rocky planet with a suitable atmosphere might maintain liquid water on its surface. The location of that zone depends strongly on the star. A hot, luminous star has a habitable zone farther away. A cooler red dwarf has one much closer in. But being located inside the habitable zone does not automatically make a planet habitable. Venus provides an excellent reminder that distance alone does not settle the matter. Atmosphere, pressure, composition, magnetic environment, geology, stellar activity, planetary rotation, and many other factors matter. A planet can sit at what looks like a promising distance and still be thoroughly unpleasant. Astronomy contains several phrases that become much less exciting once the fine print arrives. Potentially habitable is one of them. Single-star systems nevertheless offer relatively stable circumstances in which planets can sometimes maintain long-lasting orbits. The absence of a nearby stellar companion means there is no second star repeatedly altering the gravitational geometry. This can be especially important for planets at large distances from their star. A sufficiently close stellar companion could destabilize some wide planetary orbits or truncate the original planet-forming disk. A solitary star does not face that particular problem. But again, nature refuses to turn this into a simple rule that single stars are good for planets, while multiple stars are bad. Planets exist in both environments. Some binary systems have stable planets. Some single stars probably lose planets. What changes is the range of possible orbital arrangements and the history that produces them. There is also an important question hiding behind every object we currently call single. Was it always single? Stars usually form in groups inside molecular clouds. A newborn star may therefore begin life near many other stars even if none remains gravitationally bound to it permanently. Close encounters in young clusters can alter disks and planetary orbits. A star can be ejected from a group. A loosely bound pair can be separated. A multiple system can become dynamically unstable, and throw out one of its members. So a solitary star today might have had a much more social childhood. The Sun itself probably formed in a stellar nursery containing many other young stars. Evidence preserved in primitive solar system material suggests that massive stars may have existed nearby during the early stages of its formation. Those stars are long gone from our neighbourhood. Some may have exploded, others simply drifted away as the original group dispersed through the Milky Way. After billions of years, finding the Sun's original siblings is extremely difficult, because the galaxy continually mixes stellar populations. Imagine releasing thousands of people into a city and trying to reunite them 4.5 billion years later. The city also rotates. This history makes the category of single star systems more interesting than the word single suggests. It describes the arrangement we observe now, not necessarily every arrangement the star has experienced. Stars move through the galaxy. They pass other stars. Usually these encounters occur at enormous distances and cause little disturbance. Occasionally, particularly inside dense clusters, encounters can be much closer. A passing star may disturb comets or alter the outer regions of a planetary system. The central star remains single, but its surroundings are never entirely sealed away from the galaxy. The outer solar system demonstrates this nicely. Far beyond Neptune lies a vast population of icy bodies. Still farther away, astronomers infer the existence of the Oort cloud, an enormous, roughly spherical reservoir of comets extending perhaps tens of thousands of astronomical units from the Sun. Objects at such distances are only weakly attached compared with Earth or Jupiter. Passing stars and the gravitational influence of the Milky Way can perturb their orbits. Some may eventually be sent inward, becoming long-period comets. So even the Sun, our familiar solitary star, participates in a much larger gravitational environment. Single does not mean isolated from the universe. It simply means there is no bound stellar companion sharing the system in the way we see in binaries and larger stellar families. And there are many reasons a star might end up alone. Sometimes only one star forms from a collapsing region. Sometimes nearby stars form but never become permanently bound. Sometimes members of a young group separate. Sometimes a formerly multiple system may lose a component through gravitational interactions. Sometimes stellar evolution itself changes the configuration. The final population we observe in the galaxy is therefore the result of both formation and billions of years of movement. Mass plays a major role in all of this. Observations show that multiplicity generally becomes more common as stellar mass increases. Low-mass red dwarfs are frequently single. Sun-like stars have a larger fraction of companions. Very massive stars are especially likely to belong to binary or multiple systems. That pattern gives astronomers clues about how stars form. Massive stars tend to form in dense environments with large amounts of material where fragmentation can produce several stars close together. Small stars can also form in groups, but a much larger fraction end up travelling alone. So if you randomly selected a red dwarf somewhere in the Milky Way, finding it without a stellar companion would not be surprising. If you selected an extremely massive O-type star, discovering that it had company would be much less surprising. This becomes especially important when estimating how many planetary systems might exist. Red dwarfs dominate the stellar population of the galaxy. They are faint, which is why the night sky does not look filled with them despite their abundance. Many nearby red dwarfs cannot be seen without telescopes. If a large fraction of those stars are solitary, then single-star planetary environments may be extraordinarily numerous. Their planets, however, would experience conditions very different from Earth. Because red dwarfs are dim, planets receiving Earth-like amounts of stellar energy must orbit much closer to them. That means their years can be extremely short. Some planets in the temperate regions of small stars complete an orbit in days or weeks, rather than 12 months. Close orbits also increase the importance of tidal effects. A planet may become tidally locked, rotating in such a way that the same hemisphere continually faces the star. That sounds immediately catastrophic, with one side permanently illuminated and the other in darkness, but atmospheric and ocean circulation could move heat around. Whether a particular world could support stable surface conditions depends on the details. Then there is stellar activity. Red dwarfs, especially young ones, can produce powerful flares. A planet close to the star may receive intense bursts of ultraviolet and X-ray radiation. That could erode atmospheres or create difficult conditions for surface life. On the other hand, red dwarfs live for extraordinarily long periods, providing enormous amounts of time for planetary systems to evolve. There are advantages and disadvantages, which is generally what happens whenever the universe offers something that initially sounds convenient. Larger solitary stars bring different problems. A massive star may shine thousands or even millions of times more brightly than the Sun, but it consumes nuclear fuel rapidly. Its lifetime can be measured in millions rather than billions of years. That may not provide much time for slow biological evolution on surrounding planets, assuming planets can form and survive there at all. The star may eventually explode as a supernova, so brightness is not necessarily generosity. A small star gives less energy but offers extraordinary longevity. A massive star provides spectacular illumination and a very short lease. Stars like the Sun occupy a middle ground. That middle ground is part of the reason astronomers often focus on Sun-like stars when discussing Earth analogues, though there is nothing in physics saying life must prefer exactly what we do. We have a sample size of one inhabited planet. Science would prefer a slightly larger survey. Until then, single-star systems remain some of our best laboratories for understanding how planets form and how different stellar environments shape them. Barnard's star gives us a nearby red dwarf moving rapidly across our sky. Tau Ceti gives us a nearby, relatively sun-like solitary star with a notable debris environment. Epsilon Eridani offers a younger K-type system with a giant planet and substantial leftover material from its formation. And the Sun gives us the only star system we can examine closely enough to send spacecraft through it, land on its planets and moons, collect pieces of asteroids, measure its solar wind directly, and occasionally complain about its weather. Each is a single star system. None is truly simple, and that is useful, because the apparent simplicity of one central star gives us a baseline. We can see what gravity does when one star dominates. We can see where planets can form. We can study debris disks without immediately having to account for a second stellar mass. We can watch how planets tug on their host star and how a single star influences the climates and atmospheres around it. Once that baseline is understood, adding another star changes the problem in a very noticeable way. Instead of one dominant source of gravity, there are two. Instead of one stellar orbit to ignore because the star sits approximately at the centre, both stars may move dramatically around a shared point. Their distance from one another may remain wide and comfortable, or they may pass so close that their outer layers eventually interact. Planets may circle one of them. Planets may circle both. One star may age before the other and begin transferring matter across the space between them. And sometimes the two lights we see in the sky are not merely neighbours that happen to line up from our viewpoint, but partners that have been travelling through the Milky Way together for millions or billions of years. Once a second star enters the picture, the basic rules remain the same, but almost everything becomes more interesting. A binary star system consists of two stars that are gravitationally bound and orbit a common centre of mass. Neither star is simply sitting still while the other circles around it. Both are moving. If one star is much more massive than the other, the larger star may appear to move only slightly, while its smaller companion follows a much wider path. If their masses are similar, the motion becomes more balanced, with both stars tracing noticeable orbits around the point between them. That common point is the barycenter we encountered earlier. With the Sun and Earth, the barycenter is so close to the Sun's centre that saying Earth orbits the Sun works perfectly well. With two comparable stars, however, the barycenter can lie well outside either star. Imagine two people holding the ends of a long pole while turning around a point somewhere between them. One may travel in a smaller circle, and the other in a larger circle, but both are participating in the motion. Gravity keeps the arrangement together. The stars are not necessarily close. Some binary companions orbit at distances small enough that the stars almost touch. Others are separated by hundreds or thousands of astronomical units. 1 astronomical unit, or AU, is approximately the average distance between Earth and the Sun. A binary separated by 1,000 astronomical units is therefore enormously wide by solar system standards, yet the two stars can still remain gravitationally connected. The time required to complete one orbit depends on the masses of the stars and the distance between them. Close binaries may complete an orbit in hours or days. Wider pairs can take decades, centuries, or much longer. From Earth, this creates several different observational problems because a binary with an orbital period of a few hours changes rapidly, while one requiring several hundred years asks astronomers to exercise a level of patience that usually involves leaving the project to future generations. Binary stars are common enough that they cannot be treated as unusual exceptions. The likelihood that a star belongs to a multiple system depends strongly on stellar mass, with higher mass stars generally showing higher multiplicity rates than low mass stars. This is one reason astronomers have to be careful when talking about a typical star system. A typical system for a small red dwarf is not necessarily typical for a massive blue star. To understand why binaries are so common, it helps to return briefly to star formation. Stars begin inside large clouds of cold, molecular gas and dust. Gravity causes denser regions of these clouds to collapse, but a collapsing cloud is rarely perfectly uniform. It contains turbulence, rotation, density variations, and smaller concentrations of matter. As the cloud contracts, it can fragment. Instead of producing one central protostar, a collapsing region may produce two. Those young stars can remain gravitationally bound and continue evolving together. In that sense, binary stars are not usually two unrelated stars that happen to meet later and decide to stay together. Capturing another star permanently through gravity alone is difficult because some energy must be removed from the encounter. Most binaries are thought to originate through star formation processes that place the stars into a shared gravitational arrangement from an early stage. They can spend billions of years together after that. Their relationship may be distant and uneventful, or extremely close and complicated. One of the best-known binary systems in the sky is Sirius. Sirius is the brightest star in Earth's night sky, and is also known as Alpha Canis Majoris. Its primary component, Sirius A, carries catalogue designations including HD 48915 and HIP 32349. To the unaided eye, Sirius looks like a single brilliant point. In reality, Sirius A has a faint companion, Sirius B, and the pair orbit each other roughly once every 50 years. Sirius B is a white dwarf, the dense remnant of a star that completed its ordinary nuclear-burning life long ago. That combination immediately shows us something important about binaries. The two stars do not have to look alike. Sirius E is a normal main-sequence star, hotter and more luminous than the Sun. Sirius B is a stellar remnant. Both belong to the same gravitational system. The reason Sirius B is so faint is not that it lacks energy completely. White dwarfs can be extremely hot. The problem is their size. Sirius B contains a large amount of mass compressed into an object roughly comparable in size to Earth. With such a small surface area, it produces much less total light than Sirius A. If you looked only at the brightness of the system, Sirius A would dominate completely. Yet gravity reveals the companion. Before Sirius B was directly observed, astronomers had already noticed that Sirius A was not moving through space exactly as expected. Its path showed a periodic wobble, suggesting that something unseen was pulling on it. That is one of the recurring themes in astronomy. You do not always have to see an object to know it is there. If something massive causes another object to move, its gravity provides evidence. Sirius eventually became a famous example of a visual binary because both members can be resolved with suitable telescopes. But not all binaries are so cooperative. Consider 61 Cygni. This nearby pair consists of 61 Cygni A, also catalogued as HD 201091, HIP 104214, and GJ 820A, together with 61 Cygni B, catalogued as HD 201092, HIP 104217, and GJ 820B. Both stars are relatively small orange-red dwarfs, and they form a wide visual binary. The name 61 Cygni may not have the immediate recognition of Sirius, but the system has an important place in astronomy. It became famous in the 19th century because it was associated with one of the first successful measurements of stellar parallax. Parallax is the apparent shift of a nearby star against more distant background stars as Earth moves from one side of its orbit to the other. You can demonstrate the basic idea without any telescope. Hold one finger in front of your face. Close your left eye, then open it and close your right eye. Your finger seems to move against the background even though the finger has remained where it is. Earth's orbit provides astronomers with a baseline about 2 astronomical units across when observations are compared 6 months apart. Nearby stars appear to shift slightly. Farther stars shift less. From that tiny angle, astronomers can calculate distance. The shift is extremely small, which is why stellar parallax was so difficult to measure historically. But once it became possible, the enormous scale of interstellar space stopped being only an estimate and became something that could be measured geometrically. 61 Cygni was a good target because it is nearby and has a large proper motion across the sky. The binary nature of the system adds another layer because the 2 stars also move around each other. Astronomers therefore have to separate several kinds of motion: Earth's changing viewpoint, the star's motion through the galaxy, and the orbital motion of the binary itself. The sky may look calm, the calculations are less relaxed. Visual binaries like 61 Cygni are the most intuitive type because telescopes can distinguish the 2 stars and astronomers can watch their positions change over time. But there are binaries that remain unresolved even through powerful instruments. This gives us spectroscopic binaries. A spectroscope separates starlight into its component wavelengths. Dark and bright features in a stellar spectrum reveal information about temperature, composition, motion, and other properties. If a star moves toward us, its spectral features shift slightly toward shorter wavelengths. If it moves away, they shift toward longer wavelengths. In a binary system viewed at a useful angle, the stars repeatedly move toward and away from us as they orbit their shared barycenter. Their spectral lines therefore shift back and forth. Sometimes astronomers can see spectral features belonging to both stars. One set moves toward the blue while the other moves toward the red, and then the directions reverse as the stars continue around their orbit. This is called a double-line spectroscopic binary. In other systems, one star is too faint to contribute easily detectable spectral lines. Astronomers see only the brighter star's spectrum moving back and forth. That is a single-lined spectroscopic binary. Either way, an apparently solitary point of light can reveal that it contains 2 stars. The method is especially useful for close binaries because close stars often orbit rapidly and cannot be separated visually. Then there are eclipsing binaries. These are systems whose orbital planes happen to be aligned so that, from our viewpoint, one star periodically passes in front of the other. The total light from the system decreases. Later, the other star may pass in front and create another decrease. Astronomers plot these brightness changes in a light curve. The shape, timing, and depth of the eclipses can reveal a remarkable amount of information about the system. If one eclipse is much deeper than the other, the stars may have different surface temperatures or brightnesses. The duration of the eclipse gives information about sizes and orbital motion. Combine the light curve with spectroscopic measurements, and astronomers can calculate stellar masses and radii with impressive precision. Binary stars are therefore not merely interesting objects. They are measuring tools. For an isolated star, determining mass directly is difficult. With a binary, gravity does the experiment for us. Measure the orbit, determine the period and scale, apply the laws of orbital motion. The masses can be calculated. Much of what astronomers know about stellar masses has come from binary systems. That information then helps calibrate our understanding of single stars. In a useful way, two stars can tell us more about one star than one star can tell us about itself. An especially clear example of an eclipsing binary appears in the Kepler-16 system. Kepler-16 is also catalogued as KIC12644769. Its two stars, Kepler-16a and Kepler-16b, orbit each other approximately every 41 days. The larger star has about 69% of the Sun's mass, while the smaller companion has about 20%. And Kepler-16 contains something extra: a planet. Kepler-16b travels around both stars rather than orbiting just one of them. It completes an orbit in about 229 days and is roughly Saturn-sized. It became famous as the first planet definitively detected in a circumbinary orbit, meaning an orbit around both members of a binary. The comparison with the fictional planet Tatooine appeared almost immediately because a world in such a system really could have two suns in its sky. Kepler-16b itself is a gas giant, so there is no known surface on which to stand while appreciating the view. Astronomy occasionally provides the scenery and removes the viewing platform. The important point is that a binary system does not prevent planets from existing. It changes the orbital possibilities. A planet in a binary generally has two broad options. It can orbit one star while the second star remains farther away. Astronomers often call this an S-type orbit, or the planet can travel around both stars together, which is called a P-type or circumbinary orbit. Stable versions of both arrangements exist. What usually does not work well is placing a planet in an unfortunate middle region where the changing gravitational pulls of the two stars repeatedly disturb its orbit. Over long periods, such an orbit may become unstable. The planet could be thrown into a different orbit, collide with another object, fall toward one of the stars, or be ejected from the system entirely. Gravity has no concern for whether a planetary arrangement looked attractive in the original diagram. Distance matters enormously. Imagine two stars separated by hundreds of astronomical units. A planet orbiting close to one of them may spend most of its time responding primarily to its host star. The second star provides an additional gravitational influence, but one that may be weak enough for the planet's orbit to remain stable. Move the stars much closer together, and a planet orbiting only one member has less room. Bring them closer still, and stable planetary orbits may be more practical around both stars rather than around either individually. The details depend on masses, separation, orbital eccentricity, and the planet's own orbit. Binary stars themselves also come in circular and eccentric arrangements. A circular binary keeps approximately the same separation throughout its orbit. An eccentric binary does not. The stars approach more closely at one part of the orbit and move farther apart at another. That varying separation changes the gravitational environment around them. For planets, disks, and any material near the stars, the difference can matter. Young binaries can be surrounded by disks of gas and dust, just as young single stars are. Sometimes each star possesses its own small disk. Sometimes a larger disk surrounds both. Sometimes all of these structures appear together. The binary's gravity can create cavities, gaps, spirals, and other features. Planet formation must therefore operate in an environment where the central gravitational source is moving. This sounds difficult, and it is. But difficult is not the same as impossible. The discovery of planets associated with binary stars has shown that planet formation can survive conditions astronomers once expected to be more disruptive. There is another distinction that becomes increasingly important as we move from wide binaries to close ones. Two widely separated stars can evolve almost as though they were single stars. One may become a red giant while the other continues its ordinary life, but if the distance is large enough, very little material passes directly between them. Close binary stars behave differently. When a star exhausts hydrogen in its core, it can expand dramatically. A star that once fit comfortably inside its orbit may eventually swell until its outer layers approach the region where the companion's gravity becomes important. Material can then move from one star to the other. This can change both objects. The donor star loses mass. The companion gains mass. Gas may form a rotating accretion disk. The system's orbit can change. A star that would have followed one evolutionary path in isolation may experience a very different history because it has a nearby companion. This is one reason binary evolution is such a major field of astrophysics. A star's mass determines much of its life, but in a close binary, its neighbour can alter that mass. The normal rules still apply. Someone simply keeps changing the starting conditions halfway through. Some binaries eventually contain a normal star and a white dwarf, as Sirius does, although Sirius is wide enough that its present-day configuration is not one of the most extreme interacting examples. Others contain neutron stars. Some contain black holes. Matter falling onto compact objects can become hot enough to produce powerful X-rays. Two white dwarfs may orbit one another. Two neutron stars may do the same. Under certain conditions, compact binaries lose orbital energy through gravitational radiation, causing the objects to spiral gradually inward. If two neutron stars eventually merge, the event can produce gravitational waves and a brilliant kilonova, while also creating conditions where heavy elements are formed. Gold, platinum, and other heavy nuclei have histories connected to events like these, so a binary can begin as two ordinary young stars in a cloud of gas, and end billions of years later as two objects whose collision briefly becomes detectable across enormous cosmic distances. That is quite a lot of development for something that began because one collapsing cloud produced two centres instead of one. Not every binary gets such an exciting ending. Many simply continue orbiting. A good nearby example of a long-lived stellar pair is Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is catalogued as HD 12862-0 and HIP 71683. Alpha Centauri B is HD 128621 and HIP 71681. They are both relatively Sun-like stars with a somewhat more massive and brighter than the Sun, and B somewhat smaller and cooler. The pair travels around a shared barycenter in an orbit lasting roughly 8 decades. From a planet associated with one of those stars, the other would be an extraordinarily bright object in the sky. But Alpha Centauri introduces an important complication. Alpha Centauri A and B are unquestionably a binary pair, yet the complete Alpha Centauri system contains another star. Proxima Centauri, a small red dwarf and the closest individual star to the Sun, is gravitationally associated with the pair at a much greater distance. So Alpha Centauri A and B form a binary subsystem inside a larger 3-star arrangement. This is exactly where the neat categories begin overlapping. A pair of stars can be studied as a binary even when that pair belongs to something larger. In systems containing several stars, nature often arranges them hierarchically. 2 stars form a close pair, a third orbits much farther away, or 2 close binaries may orbit one another. This hierarchy helps maintain stability because it prevents every star from strongly disturbing every other star during every orbit. The difference between a binary system and a multiple star system is therefore sometimes less about completely different physics and more about adding another gravitational level. Before adding that level, however, the basic binary arrangement already gives us most of the ingredients we will need. 2 masses, 1 shared barycenter, orbital periods ranging from hours to millennia, pairs that can be wide or close, circular or eccentric, visually obvious or detectable only through spectra and eclipses, planets that may orbit one member or both, stars that can evolve independently when widely separated or exchange matter when forced into close quarters. and observational techniques that let astronomers turn those motions into direct measurements of stellar mass. Once 3 stars are involved, all of these ideas remain, but they can no longer be described with a single orbit between 2 objects. The Alpha Centauri system gives us a useful way to move beyond binaries, because it shows how nature often handles a 3rd star without turning the entire arrangement into chaos. Alpha Centauri A and Alpha Centauri B form the close central pair. Alpha Centauri A is catalogued as HD 128620 and HI P71683, while Alpha Centauri B is HD 128621 and HIP 71681. Much farther away is Proxima Centauri, also known as GJ 551 and HIP 70890. All 3 are gravitationally associated, making Alpha Centauri the nearest known triple star system to the Sun. NASA describes Proxima as the distant 3rd member of the system, while measurements of its motion support the conclusion that it is gravitationally bound to Alpha Centauri A and B. The arrangement is not 3 stars following comparable paths around one central point. That would be much harder to keep stable. Instead, the system is hierarchical. 2 stars form a relatively tight binary, and the 3rd travels around that pair at a vastly greater distance. This is one of the most important ideas in understanding systems containing 3, 4, 6, or even more stars. Stability usually comes from separating the different orbital relationships. Imagine trying to keep 3 people running around one another at roughly the same distance, with each person constantly changing the direction of the other 2. It can be done mathematically for certain carefully arranged cases, but the slightest disturbance can cause trouble. Now, change the arrangement. Let 2 people circle each other closely, while the 3rd walks around them from much farther away. The inner motion can continue relatively undisturbed, while the distant 3rd person mostly responds to the combined mass of the inner pair. That is much closer to the architecture astronomers commonly find. The inner binary behaves approximately like one gravitational object when viewed from a great distance. The 3rd star follows a much larger outer orbit around the very centre of the whole system. Of course, approximately is doing some useful work there. The 3rd star still influences the inner pair. The inner stars influence the outer orbit. Nothing is completely independent, but the large difference in scale keeps those interactions from becoming immediately destructive. Alpha Centauri demonstrates this very well. A and B orbit each other in roughly 8 decades. Proxima Centauri, by comparison, is so distant that one journey around the inner pair takes hundreds of thousands of years. NASA notes that Proxima's orbit around the other 2 takes more than 500,000 years. One orbit is therefore short enough for astronomers to watch a meaningful fraction of it during modern observational history. The other is long enough that entire human civilizations occupy tiny fractions of one lap. Both belong to the same system. This enormous range of timescales becomes normal once more stars are added. A triple system can have an inner orbital period of days and an outer period of centuries. A quadruple system might consist of 2 binaries, with each binary completing rapid internal orbits, while both pairs take decades or centuries to circle one another. Larger systems can add another level beyond that. Nature seems to enjoy nesting orbits. It also saves everyone a considerable amount of gravitational confusion. A second well-known triple system is hanging in a part of the sky that many people have looked at without realizing there was anything complicated about it. Polaris, the North Star, is Alpha Ursae Minoris. It is also catalogued as HD 889, O and HIP 11767. To casual observation, Polaris is 1 star. It is actually 3. The dominant star, Polaris AA, is the bright Cepheid variable we associate with the North Star. A very close companion, Polaris AB, orbits nearby, while a much more distant companion called Polaris B lies farther out. Hubble directly imaged the close companion, confirming visually an object whose existence had already been inferred from its gravitational effects. NASA describes Polaris explicitly as a triple star system. Polaris is useful because it shows how easily multiplicity can hide. One companion is wide enough to be separated with modest telescopes. The other is so close to the bright primary that resolving it directly required Hubble. If you were limited to the unaided eye, the entire system would simply be one familiar point marking approximately north. That means the number of stars we think we see, and the number of stars actually present, can be very different. This becomes particularly important in surveys of distant stellar populations. Suppose a telescope observes what appears to be one star. If that point is really 2 or 3 unresolved stars, estimates of brightness, mass, age, or distance can become more complicated. Astronomers therefore use several methods to uncover hidden companions. Direct imaging works when stars are sufficiently separated. Spectroscopy reveals changing radial velocities when stars orbit too closely to resolve. Eclipses cause measurable dips in brightness when one star passes in front of another. Astrometry can reveal small positional wobbles. Over long periods, common proper motion can show that stars separated widely in the sky are moving through space together rather than simply appearing close by coincidence. Multiple star astronomy is partly the science of asking whether the point of light has been telling the whole truth. Polaris also introduces another useful feature of these systems. The stars do not have to be identical. They can have different masses, temperatures, brightnesses, and evolutionary states. Because stellar lifetime depends strongly on mass, the most massive member can evolve much faster than its companions. A system can therefore eventually contain a giant star beside smaller main sequence stars, or a white dwarf beside stars that are still steadily burning hydrogen. That situation is especially clear in 40 Eridani. 40 Eridani, also known as Omicron 2 Eridani, is a nearby triple system. Its primary, 40 Eridani A, is also called CADE and carries the catalogue designation HD26965 and HIP 19849. Farther away from A is a close pair consisting of 40 Eridani B, a white dwarf, and 40 Eridani C, a red dwarf. NASA describes the system as 3 stars, with B and C forming the binary pair at a distance from A. That is already more varied than Alpha Centauri. 40 Eridani A is an ordinary main sequence star smaller and cooler than the Sun. 40 Eridani C is a much smaller red dwarf. 40 Eridani B is not an ordinary star at all in the usual main sequence sense. It is a white dwarf, the compact exposed remnant of a star that once passed through a much more active stage of stellar evolution. All 3 remain gravitationally connected, so a multiple system can preserve a record of different stages of stellar life at the same time. The white dwarf was once a normal star. It evolved, expanded, shed its outer layers, and ended as a compact remnant. Its companions remained. From the standpoint of the system, one member changed dramatically while the wider gravitational structure survived. A sufficiently long-lived multiple system can therefore become a kind of comparison experiment. The stars presumably formed at roughly the same time and from similar original material, but their different masses caused them to evolve at different rates. Astronomers can use that fact to test models of stellar evolution. It is a little like meeting siblings of the same age and finding that one has somehow completed several entire careers while another is still considering what to have for breakfast. Mass is responsible for much of the difference. A more massive star has more nuclear fuel, but it uses that fuel much faster. A smaller star has less fuel and consumes it more slowly. In multiple systems, those different clocks run side by side. Another famous triple system behaves very differently again. Algol, Beta Persei, is catalogued as HD 19356 and HIP 14576. For centuries it was known because its brightness changes noticeably. Algol A and Algol B form a close eclipsing binary, while Algol C orbits the inner pair at a greater distance. Simbad lists Algol under HD 19356 and HIP 14576 and identifies the A, B and C components associated with the system. The inner pair passes in front of one another from our viewpoint. causing periodic changes in the total light. But Algol is more than a convenient eclipsing system. It helped astronomers understand how mass transfer can change stellar evolution. The less massive star in the close pair is more evolved than the more massive one. At first glance, that seems backward. More massive stars should evolve faster. The solution is that the currently less massive star was originally the more massive one. It evolved first, expanded, and began transferring material to its companion. The companion gained mass. The donor lost it. What astronomers see today is therefore not the original mass arrangement. This became known as the Algol paradox. The paradox disappears once binary interaction is included. Add a third star and the overall system becomes even more instructive, because you now have a close interacting pair existing inside a wider triple arrangement. The outer companion does not need to participate directly in the mass transfer to influence the long-term dynamics. This brings us to a phenomenon that can become important in hierarchical triples. If the outer orbit is strongly tilted relative to the inner orbit, the third star's gravity can slowly change the shape and orientation of the inner binary's orbit. Under suitable conditions, the inner orbit can become more eccentric while its inclination changes, and then later reverse the process. This family of effects is associated with what astronomers call quasi-leadoff oscillations. The stars are not rapidly yanked from one orbit to another. The changes occur gradually over many orbital cycles, but given millions or billions of years, gradual changes are perfectly capable of becoming important. An initially comfortable pair can be driven into a much more elongated orbit. During the closest part of that orbit, the stars may pass near enough for tides to become significant. Tidal interactions can remove orbital energy. The binary can tighten. Eventually, two stars that began relatively far apart may end up in an extremely close configuration, partly because a third star spent a very long time quietly interfering. This is one reason triple systems matter beyond simply counting stars. A distant companion can alter the future of an inner binary without ever coming particularly close to it. The system is hierarchical, but not disconnected. The same principle can affect planets. A distant stellar companion can change planetary eccentricities or orbital inclinations over long timescales. In some systems, those perturbations may destabilize planets. In others, stable regions remain available for billions of years. As usual, the answer depends on masses, distances, orientations, and the particular orbital architecture. Gravity remains very consistent about refusing to provide one simple rule for every system. Triple stars are only the beginning. A very useful example of a four-star system is HD 9880, also known as HIP 55505 TWA4, and the variable star designation TV Craterus. HD 98800 contains four young stars arranged as two binaries. Those two binary pairs are themselves gravitationally bound to one another. NASA describes HD 9880 as a quadruple system containing two double-star pairs, with the two pairs separated by roughly 50 astronomical units. One of the binaries is surrounded by a dusty disk. This is hierarchy made particularly easy to picture. Start with two stars. They orbit each other. Some distance away, another two stars do the same. Now take those two binaries and place them into a much wider mutual orbit. The result is four stars, but the system does not behave as though four equal objects are constantly passing among one another. On short timescales, each star responds strongly to its close partner. On longer timescales, each binary responds to the gravitational influence of the other pair. You can think of the system as having layers of motion. Watch briefly and you mainly notice the closed binary orbits. Watch for longer and the larger architecture becomes apparent. The dusty material around part of HD 98800 makes the system especially useful for understanding how planet-forming environments behave when several stars are involved. A disk around a single star already experiences internal collisions, gas motion, magnetic activity, and gravitational effects from forming planets. Put that disk inside a quadruple system, and there are additional stellar perturbations to consider. The companion stars can influence the disk's size and shape. They can help create gaps or alter the orientation of the material, and yet the disk survives. This is worth remembering because early discussions of multiple stars sometimes treated them as difficult places for planets. They certainly can be difficult. They're not necessarily sterile. The universe has repeatedly demonstrated that planet formation is willing to attempt the job under conditions that would make a project manager request a revised schedule. 4-star systems can take other hierarchical forms as well. One common arrangement is a triple-like structure with a close binary plus 2 increasingly distant companions. Another is the 2 binaries arrangement we see in HD 98800. Whether such systems remain stable depends heavily on how clearly separated the orbital scales are. If 2 binaries come too close, individual stars begin strongly disturbing members of the opposite pair. The neat hierarchy starts breaking down. Close encounters can exchange partners. A star can be ejected. A binary can tighten. The entire configuration can rearrange itself. In dense stellar environments, these encounters are particularly important. A star cluster contains many systems moving past one another, and although stars themselves are tiny compared with the distances separating them, wide multiple systems can be gravitationally fragile. The widest companions may eventually be stripped away. Tighter inner binaries are much harder to disrupt. This means the multiple systems we observe today are partly survivors of their environments. Some were probably born in one arrangement and later altered. Others may have lost additional companions. A system we currently call triple might once have contained 4 members. A wide binary might be what remains after a former triple expelled one star. Dynamical evolution can be untidy. Fortunately, it usually takes place slowly enough that nobody has to clean up immediately. We can increase the star count again with one of the brightest examples in the night sky. Castor Alpha Geminorum is also associated with the catalogue designations HIP 3685, O and the Washington double star designation WDSJ 07346 plus 3153AB. Castor appears to the unaided eye as one bright star in Gemini, but the complete system contains 6 stars. 6. And it does not achieve that by placing 6 stars into one crowded orbital scramble. Castor is organized into 3 pairs. Castor A is itself a spectroscopic binary. Castor B is another spectroscopic binary. A and B form a wider visual pair. A third component known as Castor C, or YY Geminorum, is also a binary. That third pair travels around the inner 4 at much greater distance. So when someone points toward Castor and says, "that star," the universe has technically given them 6 opportunities to be more specific. The impressive part is not simply the number, it is the architecture. Binary inside wider binary relationships, followed by another binary at a larger scale. The pattern is exactly what long-term stability would encourage. Close relationships are kept close. Wide relationships remain wide. The orbital hierarchy reduces dangerous encounters. Castor also reminds us that the apparent brightness of a multiple system can be misleading. From Earth, all of those stars contribute in different amounts to what we see. Some are easy to separate with telescopes. Some reveal themselves only spectroscopically. Our classification of the system became more complicated as observational methods improved. In other words, Castor did not acquire additional stars. We became better at noticing them. A similar lesson appears in another familiar naked eye pairing, Mizar and Alcor in the handle of the Big Dipper. Mizar is Zeta Ursae Majoris and includes the designation HIP 65378. Its bright component Mizar A is also listed as HD 116656. Alcor, nearby in the sky, is 80, Ursae Majoris, HD 116842, and HIP 65477. Together, the larger Mizar-Alcor association is understood as a 6-star arrangement. Mizar A is a spectroscopic binary. Mizar B is also a binary, and Alcor has a faint companion of its own. This system is particularly enjoyable because people have been using Mizar and Alcor as a naked eye vision test for centuries. With good eyesight under a suitable sky, you can separate Mizar and Alcor without a telescope. Then a telescope reveals that Mizar itself is double. Then spectroscopy reveals still more stars. The apparently simple test of whether you can see 2 points ultimately leads to 6 stars. Astronomy has a habit of rewarding closer inspection by making the situation less convenient. Mizar and Alcor also illustrate the problem of determining whether widely separated stars are truly part of one gravitational system, or merely moving together as members of a larger stellar group. Wide associations can be difficult to characterize because the orbital periods are extremely long, and the gravitational binding can be relatively weak. Astronomers compare distances, velocities, proper motions, and other measurements to determine whether the components share a physical relationship. The farther apart two stars are, the more important this becomes. Two unrelated stars can appear close together on the sky simply because one happens to lie behind the other from Earth's viewpoint. This is called an optical double. A true multiple star system requires a physical relationship, not just convenient alignment. That distinction becomes especially important when working with huge catalogues containing billions of measured stars. Then we arrive at a system that seems almost designed to demonstrate how far hierarchy can be taken. TYC 7037-89-1, also known as TIC 16878980, contains 6 gravitationally bound stars arranged as 3 eclipsing binaries. NASA describes it as the first known 6-star system in which all 6 stars participate in eclipses visible from our line of sight. The A and C binaries have orbital periods of roughly a day and a half, and those 2 binaries orbit each other in about 4 years. The B binary has a period of roughly 8 days, and travels around the inner 4 stars on an orbit estimated at about 2,000 years. This is hierarchy almost in textbook form. Pair A, 2 stars. Pair C, 2 stars. Those 2 pairs orbit each other. Pair B, 2 more stars. That outer pair then orbits the 4-star inner structure. 6 stars, 3 type binaries, 1 intermediate orbit, and 1 enormous outer orbit. Because all 3 inner pairs eclipse from our viewpoint, astronomers receive a great deal of information. Every eclipse changes the total brightness. The timing of those changes gives orbital periods. The shapes of the dips help constrain stellar sizes. Spectroscopy provides velocities. Combining the measurements allows astronomers to estimate masses, temperatures, separations, and other properties. Usually, a complicated system creates an observational headache. TC 7037-89-1 manages to be complicated in a very helpful way. The alignments provide repeated measurements of all 3 binaries. NASA researchers even used automated analysis of test-like curves to help identify the system among enormous numbers of stars. This is increasingly how multiple systems are found. A human astronomer does not simply look through a telescope until 6 stars happen to appear in a pleasing arrangement. Space telescopes collect enormous time series data sets. Computers search for repeated brightness patterns. Candidates are examined. Ground-based telescopes provide follow-up observations. Spectra are measured. Positions are checked. What begins as a strange repeating set of dips can eventually become a detailed map of several stars orbiting one another. There is also an interesting statistical question hiding behind all of these examples. How many stars can realistically remain bound in one stable stellar system? There is no simple small number limit such as 3, 4, or 6. NASA notes that systems containing as many as 7 stars have been observed, but systems become increasingly uncommon as the number of components rises. This makes sense. Every additional star requires another stable place in the hierarchy. It also creates more opportunities for gravitational interactions to rearrange or disrupt the system. A binary needs one relationship. A stable triple usually needs an inner binary and a separated outer orbit. Outer. A quadruple may require 2 binaries or several nested levels. By the time 6 or 7 stars remain permanently bound, the architecture tends to look less like a crowd and more like a carefully organized collection of smaller systems. That organization can begin during formation. A collapsing molecular cloud can fragment into several dense cores. A circumstellar or circumbinary disk can fragment as well. Young stars interact while still embedded in gas. Some components migrate inward, others move outward. Gas can remove energy from stellar orbits, helping pairs tighten. Gravitational encounters may eject the least strongly bound member. The system that survives after the surrounding gas disappears may be much simpler than the original group. This is one reason astronomers study very young multiple systems. They provide evidence about how stellar families assemble before billions of years of evolution erase the early details. The final arrangement also depends on the environment. In a sparse region, a wide tertiary companion may survive for a very long time. Inside a dense star cluster, passing stars can disturb the outer orbit. A weakly bound companion may be stripped away. The close inner binary survives because its components are held together much more strongly. Over time, clusters can therefore process their multiple systems, removing wide companions and modifying orbital distributions. Multiplicity is not merely something stars are born with, it can evolve. The stars themselves evolve too. Imagine a stable triple containing 3 ordinary main sequence stars. The most massive star exhausts its central hydrogen first, it expands. If it belongs to a close inner pair, it may transfer material to its companion. That interaction can change the orbital period and stellar masses. The evolved star may eventually become a white dwarf. Later, its companion evolves. Farther out, the third star may still look almost unchanged. If the inner pair eventually becomes 2 compact objects, the distant third star can continue orbiting them. Under suitable conditions, the third star's long-term gravitational influence can even help change the eccentricity of the compact binary, affecting whether the 2 objects eventually merge. So systems containing 3 or more stars are not frozen mechanical models. Their architectures can survive while the identities of the objects inside them change completely. A system might begin with 3 ordinary stars. Later it could contain a main sequence star, a white dwarf, and another evolved star. Eventually it might contain several stellar remnants. The hierarchy remains recognizable even though the stars no longer resemble their younger selves. Planets make all of this more complicated again. We already know that Proxima Centauri, the outer member of the Alpha Centauri triple system, hosts at least 1 confirmed planet. NASA specifically points to Proxima's planet when discussing planets in triple star systems. That immediately answers one basic question. Yes, planets can exist in systems containing 3 stars, but there are many ways to arrange them. A planet might orbit one star tightly, while the other stars remain far away. It might orbit a close binary with a third star farther out. In principle, a sufficiently distant planet could orbit the combined mass of an entire inner multiple system. The key is again hierarchy. Stable planets generally need an orbit where one gravitational relationship dominates. If a planet sits where 2 or 3 stars tug on it with comparable strength and rapidly changing directions, long-term stability becomes much harder. But if the planet orbits close to one star while other stars remain distant, its motion can remain reasonably regular. Or if it circles a tight binary from far enough away, the 2 stars can behave gravitationally almost like one central mass. This is why multiple star systems do not eliminate planetary systems. They create additional categories of them. And once planets are included, asking how many stars a system contains is no longer enough. We also have to ask which object the planet actually orbits, how close the stellar companions are, how eccentric those stellar orbits become, whether the orbital planes are aligned, how the stars evolved, and whether the planet formed where we currently see it or migrated there later. A single star might have no known planets at all. Another might have one giant planet moving through a tight orbit. A third could have several rocky worlds packed into a space smaller than the orbit of Mercury. Somewhere else, enormous gas giants may travel so far from their star that a single year lasts centuries. All of these are planetary star systems. The basic definition is straightforward. A planetary system consists of planets and other non-stellar objects gravitationally associated with a star, or sometimes with more than one star. The smaller objects can include moons, asteroids, comets, dust, and the leftover debris of planet formation. Our solar system is the example we know in detail. It contains 4 relatively small rocky planets close to the Sun, followed by 4 much larger outer planets. Beyond Neptune are dwarf planets and countless icy bodies. The asteroid belt lies between Mars and Jupiter, while still more distant populations extend into the outer solar system. Because we grew up inside this arrangement, it is tempting to assume that planetary systems naturally develop in roughly the same order. Small planets close in, giant planets farther out, mostly circular orbits, everything moving in approximately the same plane, a reasonably large amount of personal space between neighbours. The first discoveries of planets around other normal stars made it clear very quickly that the universe had not received that particular set of instructions. Some of the earliest exoplanets found around Sun-like stars were giant worlds orbiting extremely close to their stars. These became known as hot Jupiters. A planet with Jupiter's approximate scale sounded familiar enough. Putting it into an orbit completed in only a few days did not. Jupiter takes nearly 12 Earth years to travel around the Sun. A hot Jupiter can circle its star in less time than many people take to remember where they left an important piece of paperwork. This discovery immediately created a problem for simple models of planetary formation. Giant planets are thought to form most easily in the colder outer regions of protoplanetary disks, where solid material, including ice, is abundant enough to help build a large core. Once that core becomes sufficiently massive, it can gather enormous amounts of hydrogen and helium from the surrounding disk. If giant planets form far from their stars, why were astronomers finding them extremely close in? The answer appears to involve migration. Planets do not necessarily remain where they were born. A young planet embedded in a disk of gas interacts gravitationally with that material. Those interactions can exchange angular momentum between the planet and the disk, changing the planet's orbit. Other planets can also interact with one another. A system containing several massive worlds may experience close gravitational encounters. One planet can be thrown outward, while another moves inward. In more extreme cases, a planet can be ejected from the system entirely. The planetary system we observe today may therefore be very different from the arrangement that existed shortly after formation. This idea changed the way astronomers interpret planetary architecture. An orbit is not just an address, it can be part of a history. A planet close to a star may have formed there, migrated there gradually, or reached that region after interactions with other planets. A planet on a very eccentric orbit may preserve evidence of an unstable past. A suspiciously empty gap between planets might indicate that something formed there and later moved. Even our own solar system probably experienced substantial migration among the giant planets during its early history. The neat arrangement we see now should not be mistaken for a system that spent 4.6 billion years politely refusing to rearrange the furniture. One of the clearest examples of just how compact a planetary system can become is Kepler-11. Kepler-11 is also identified as KIC 654192. 6 confirmed planets orbit the star, and the system became famous because the planets are packed unusually close together. 5 of the 6 orbit closer to Kepler-11 than Mercury orbits the Sun. NASA describes it as one of the classic examples of a tightly packed multi-planet system. Imagine trying to place several planets into the inner region of our solar system while keeping their orbits stable. It sounds crowded, but crowded does not automatically mean chaotic. If the planetary masses, separations and orbital periods are arranged appropriately, several planets can remain close to one another for very long periods. The planets continually pull on each other, of course. That gravitational interaction can actually help astronomers measure them. When several planets transit the same star, their passages do not always occur at perfectly regular intervals. One planet can accelerate or delay another slightly through gravity. These small differences are called transit timing variations. By measuring them carefully, astronomers can estimate planetary masses and study interactions that would otherwise be invisible. The planets are effectively disturbing one another on schedule. For astronomers, this is very considerate. Transit observations have transformed our understanding of planetary systems because they allow large numbers of planets to be detected using a relatively simple geometric effect. A planet passes between its star and our telescope. The planet blocks a tiny fraction of the starlight. The brightness drops, then it returns to normal. If the same dip occurs repeatedly at regular intervals, the orbital period can be measured. The amount of light blocked gives information about the planet's size relative to the star. The method has one obvious limitation. The orbit must be aligned correctly from our point of view. Most planetary systems are not. If Earth were observing an exact copy of our solar system from a random direction, there would be a good chance that none of its planets would pass directly across the Sun from that viewpoint. That means every detection method gives us a somewhat biased sample. Transit surveys are especially good at finding planets with short orbital periods, because those planets cross their stars frequently. A planet completing an orbit every 3 days provides many chances to observe a transit. A Jupiter analogue taking nearly 12 years to complete an orbit is much less cooperative. You may have to wait more than a decade just to observe a second transit. Astronomers do occasionally demonstrate remarkable patience, but telescope proposals usually benefit from results arriving before retirement. The radial velocity method provides another view. Instead of watching for a planet to block light, astronomers measure the star's movement caused by the planet's gravity. A massive planet close to its star creates a relatively strong signal. A small Earth-like planet far from its star creates a much weaker one. For this reason, the earlier surveys were strongly biased toward large planets in close orbits. That observational bias initially made planetary systems seem stranger than they really were. It was rather like standing beside a motorway, noticing that most vehicles you can hear are large lorries, and concluding that bicycles must be extremely rare. The quieter objects are simply harder to detect. As instruments improved and observations continued for longer periods, smaller planets began appearing in large numbers. Then came another surprise. The galaxy contains many planets of sizes that our own solar system does not possess. These include super-Earths, generally larger than Earth but smaller than Neptune, and mini-Neptunes, worlds that occupy a similar intermediate range but likely possess substantial volatile envelopes. The exact terminology can vary depending on size, mass, and composition. What matters is that planets between Earth and Neptune in size are common among known exoplanet populations. Our solar system has no example. Earth is the largest rocky planet here. Neptune is almost 4 times Earth's diameter. There is an empty size range between them. Elsewhere, that range is heavily populated. This is one of the reasons astronomers have stopped treating the solar system as a universal template. It is one example, a very useful example because we can examine it closely, but still only one. Some of the most extraordinary planetary arrangements occur around stars far smaller than the Sun. TRAPPIST-1 is an ultra-cool red dwarf about 40 light-years away. It is also catalogued as 2MAS-SJ 230622928-0502-285 and Gaia DR 3263544769 08753563008. 7 roughly Earth-sized planets are known to orbit it, named TRAPPIST-1b through TRAPPIST-1h. All 7 planets would fit inside Mercury's orbit if the system were placed around the Sun. That sounds as though they should be unbearably hot. They are not, because TRAPPIST-1 is much cooler and much less luminous than the Sun. Several of the planets receive amounts of stellar energy that make them interesting when discussing the possibility of surface liquid water under suitable atmospheric conditions. NASA identifies TRAPPIST-1e, F, and G within the star's traditional habitable zone. The phrase habitable zone needs careful handling. It does not mean inhabited, it does not even mean definitely habitable. It refers to a range of distances where a planet with appropriate atmospheric conditions could potentially maintain liquid water on its surface. A planet inside that region might have no atmosphere. It could have an atmosphere far too thick. Its water could be locked beneath ice. Its star might produce damaging radiation. The planet could be geologically inactive, chemically unsuitable, or simply unpleasant in some way we have not thought of yet. Calling something potentially habitable is therefore a starting point, not a property advertisement. TRAPPIST-1 is valuable for another reason. Its planets form a tightly connected orbital chain. Their periods are related in a pattern of near resonances. Orbital resonance occurs when the periods of neighbouring bodies form simple numerical relationships. For example, one planet might complete roughly 3 orbits. In the time another completes 2. These repeated gravitational alignments can help maintain a system's architecture. They also preserve clues about migration. If several planets formed farther out and moved inward through a disk, their gravitational interactions could capture them into resonances. The final pattern can therefore contain information about how the system assembled. Something similar occurs in our own solar system. Pluto and Neptune have a 3:2 resonance. Pluto completes 2 orbits for every 3 completed by Neptune. That relationship helps prevent close encounters despite Pluto's orbit crossing inside Neptune's orbital distance in one part of its path. Jupiter's moons, Io, Europa, and Ganymede participate in another famous resonance. For every orbit completed by Ganymede, Europa completes roughly 2, and Io completes roughly 4. The universe is quite comfortable with fractions as long as gravity keeps the accounts. Multi-planet systems reveal these relationships particularly well because every world becomes part of the evidence. A single detected planet tells us something about one orbit. 7 planets tell us about an architecture. Their spacing matters, their sizes matter, their orbital periods matter, their eccentricities and inclinations matter. If the system is young enough, disks of dust may add another record of its history. Another well-known planetary system gives us a very different arrangement. 55 Cancri, also called Rho 1 Cancri and Copernicus, is catalogued as HD 75732 and HIP 43587. 5 planets are known around the star, named 55 Cancri B, C, D, E, and F. Simbad lists all 5 planetary objects with the host, while NASA uses 55 Cancri as an example of a substantial nearby multi-planet system. One member, 55 Cancri E, is especially famous. It is a super-Earth in an extremely close orbit. Its year lasts less than 1 Earth day. Think about that for a moment. On Earth, a year contains more than 365 days. On 55 Cancri E, the planet completes an entire trip around its star before Earth has finished one ordinary Tuesday. The planet is intensely heated and is certainly not an Earth twin despite being rocky in scale. This is another useful reminder that similar size does not mean similar environment. A planet can be only somewhat larger than Earth and still live under conditions entirely unlike anything on our surface. 55 Cancri also demonstrates how one system can contain several very different kinds of orbits. Planetary systems are not necessarily collections of similar worlds evenly spaced around a star. One system may contain an extremely close rocky planet, intermediate planets farther out, and a giant planet on a much wider orbit. The architecture can span large ranges of distance and orbital period. At the opposite observational extreme from transit systems are planets we can actually image. Direct imaging is difficult because stars are enormously brighter than planets. Imagine trying to photograph a firefly beside a searchlight from many kilometers away. Then make the firefly much fainter and move everything several light years farther away. That gives a rough sense of why astronomers usually prefer indirect methods. Direct imaging works best for certain young massive planets that orbit far from their stars. Young giant planets retain heat from formation and can glow strongly in infrared wavelengths. Wide separation makes it easier to distinguish the planet's light from the star's glare. One of the most famous examples is HR 8799, also catalogued as HD 218396 and HIP 114189. Four known giant planets, HR 8799b, C, D, and E, have been directly imaged around it. Simbad confirms the stellar catalogue designations, and observations with ground-based telescopes and the James Webb Space Telescope have allowed astronomers to study the four planets individually. This is very different from detecting a tiny periodic dip in brightness. We actually receive light from the planets themselves. Researchers have even combined observations taken over several years to show the four worlds moving along their orbits. The outermost planet takes centuries to circle the star, so nobody is producing a complete orbital movie anytime soon. What we have instead is a short section of a very long movement. Even that is remarkable. For most of human history, planets around other stars belonged entirely to speculation. Now astronomers can watch several of them change position around the same star. HR 8799 also contains a debris disk. That combination, young star, giant planets, and surrounding debris, gives astronomers an opportunity to study how massive planets interact with leftover material. Planets can sculpt disks. Their gravity clears some regions while concentrating material in others. By comparing a disk's shape with planetary positions, astronomers can reconstruct parts of the system's dynamics. Sometimes a planet may be inferred from a disk before the planet itself is clearly observed. Again, gravity leaves fingerprints. Not every planetary system needs to be crowded. Some stars have only one confirmed planet, although this does not necessarily mean they truly have only one. Detection limits matter. A system listed today with one known planet may gain several more after better observations. Small planets are especially easy to miss. Long-period planets may require decades of monitoring. Worlds whose orbital planes do not produce transits can remain invisible to transit surveys. A complete census is therefore difficult. When astronomers say that a system contains 3 planets, the safest interpretation is often that 3 planets have been confirmed. Nature has not signed a document promising there are no others. This distinction has become increasingly important as planetary discoveries accumulate. The number of confirmed exoplanets has grown enormously, but the larger scientific goal is not simply to collect names. Astronomers want to understand populations. How common are Earth-sized planets? How common are giant planets? How does the host star's mass affect the planets that form? How do planetary systems change with stellar composition? Which arrangements are stable? How often do planets migrate? How unusual is the solar system? The answers require studying systems rather than isolated discoveries. Suppose we detect a hot Jupiter. That is interesting. Now ask whether smaller planets survive nearby. Ask whether the giant planet's orbit is aligned with the star's rotation. Ask whether its orbit is circular or eccentric. Ask whether another distant giant planet exists. Suddenly the system becomes a record of formation and migration, rather than a single unusual object. The alignment between planetary orbits and stellar rotation can be particularly revealing. Planets form in disks, and disks generally rotate around the same axis as their young stars. We might therefore expect planets to stay approximately in that plane. Many do. Some do not. Astronomers have found planets travelling in highly tilted or even retrograde orbits relative to their star's rotation. A retrograde planet moves in the opposite orbital direction from the star's spin. That is difficult to explain through quiet formation in a flat disk alone. Gravitational interactions, additional planets, distant stellar companions, or other dynamical processes may have altered the orbit later. A badly tilted orbit is therefore not just strange geometry, it can be evidence that something happened. Planetary eccentricity tells a similar story. Earth's orbit is close to circular. Many exoplanets have significantly elongated orbits. A planet on an eccentric path experiences changing distance from its star throughout its year. At the closest point, stellar heating increases. At the farthest point, it decreases. For a world with an atmosphere that can produce unusual seasonal effects, for astronomers, eccentricity can also indicate a history of gravitational interactions. Several giant planets may once have occupied unstable orbits. Close encounters could leave survivors on eccentric paths while ejecting other worlds. Some planetary systems may therefore contain missing members. The planets we see are the ones that remained. There could be enormous numbers of former planets wandering through interstellar space after being removed from their original systems. These are called rogue planets, when they are no longer gravitationally bound to a star. They do not technically belong to planetary star systems anymore, but their existence is connected to how those systems evolve. A young planetary system can be an efficient producer of both planets and former planets. Our own system may have lost objects during its early history as well. Computer models of giant planet migration often involve gravitational reshuffling, scattering of smaller bodies, and sometimes the removal of additional planetary embryos. We cannot rewind the solar system to watch what happened. Instead, astronomers combine present-day orbits, meteorites, asteroid populations, crater histories, computer models, and comparisons with young systems elsewhere. Other stars provide different stages of the process. A protoplanetary disk shows material before planets have fully assembled. A young system such as HR 8799 shows massive planets, while considerable debris remains. Older systems show what survives after billions of years. Taken together, they provide something like a collection of snapshots from different households, rather than a complete film of one household growing old. That comparison is especially useful because planet formation happens much faster than stellar lifetimes. The main assembly of planets occurs during the early life of a star, while gas remains in the surrounding disk. The gas disk itself lasts only a small fraction of the star's total lifetime. Giant planets need to accumulate their gas before that material disappears. Rocky planets can continue colliding and assembling after much of the gas is gone. Later migration and gravitational interactions can continue for much longer. A mature planetary system is therefore the result of several stages. First comes the disk, then solid material begins growing. Planetary cores develop. Gas giants may gather thick atmospheres, orbits change, planets interact. Debris is cleared or scattered. Some worlds survive where they formed, others move. Eventually the system settles into an arrangement stable enough to persist for long periods. Settles does not mean completely stops changing. Earth's orbit is influenced continually by the other planets. The orientations of planetary orbits shift over long periods. Asteroids are perturbed. Comets enter and leave the inner solar system. The sun gradually changes. Given enough time, even stable systems evolve. The crucial difference is that their changes no longer involve immediate catastrophic rearrangement. A mature system can remain recognizable for billions of years. This is why orbital stability matters so much when discussing possible environments for life. Life on Earth required very long stretches of time. If a planet's orbit repeatedly changed drastically, if it were thrown between hot and cold regions, or if another planet eventually ejected it from the system, long-term surface stability could become difficult. That does not mean life requires a perfectly circular Earth-like orbit. It means the architecture of the entire system matters. A planet does not experience its star in isolation. It experiences neighbouring planets, moons, impacts, tides, stellar activity, and the history that produced its current orbit. Even Jupiter has generated continuing discussion about its influence on Earth. It can scatter comets and asteroids, sometimes that sends objects away from the inner solar system. Sometimes gravitational interactions can redirect objects inward. Calling Jupiter simply Earth's shield is therefore too simplistic. Large planets reshape the distribution of smaller bodies in complicated ways. Every substantial planet contributes to the gravitational character of its system. Then there is the question that almost inevitably appears whenever we discover several roughly Earth-sized planets. Could one of them contain life? The scientifically useful answer is that we need more information. Planetary size is only the beginning. Mass tells us about density. Density helps constrain composition. Atmospheric spectra can reveal gases. Stellar radiation affects atmospheric survival. Temperature estimates depend on reflectivity and greenhouse effects. Geology can influence long-term climate. Magnetic fields may affect interactions with stellar winds. Water matters, but so do carbon chemistry, energy sources and stability over time. Even the term Earth-like can be misleading. An Earth-sized planet might be nothing like Earth beyond diameter. It could be a dry rock, a global ocean, a high-pressure world, a planet with a crushing carbon dioxide atmosphere, a bare surface exposed to space, or something that does not fit comfortably into any solar system category. That uncertainty is part of why systems such as TRAPPIST-1 receive so much attention. 7 similarly sized planets around the same star create a natural comparison. They formed from the same broad environment. They receive different amounts of stellar energy because they orbit at different distances. Comparing their atmospheres, masses and compositions can reveal how neighbouring worlds diverge. The same idea applies to every multi-planet system. One planet is interesting. Several planets around the same star allow comparison while holding the star itself roughly constant. The host star is the common laboratory lamp. The planets are different experiments sitting at different distances. Our solar system has been doing this experiment for billions of years. Mercury became a heavily cratered world with extreme temperature changes. Venus developed a dense carbon dioxide atmosphere and severe greenhouse conditions. Earth retained oceans and life. Mars lost much of its early atmosphere and surface water. Jupiter and Saturn became gas giants. Uranus and Neptune developed as ice giants, with different internal compositions and histories. All formed around one star from the same original disk, yet their outcomes were dramatically different. Exoplanetary systems tell us that the possible outcomes are broader still. There are hot Jupiters almost touching their stars by solar system standards. Super-Earths, for which we have no local equivalent. Compact chains of rocky planets, highly eccentric giants, planets orbiting pulsars, young glowing giants that can be photographed directly, systems with enormous debris structures, and almost certainly categories that current telescopes are still poor at detecting. The more planetary systems astronomers find, the less useful it becomes to ask whether one is normal without defining what normal means. Normal for a red dwarf, normal for a sun-like star, normal for a young system. Normal among systems our current methods are capable of detecting. Our surveys are still incomplete. What they already show is that planet formation is not a machine that produces one standard arrangement. It behaves more like a process with a common set of physical rules and a very large number of possible results. Gravity is always present. Conservation of angular momentum still applies. Gas behaves according to the same physics. Dust grains collide. Planets exchange momentum. Stars provide radiation. Nothing is breaking the rules. The variety comes from different starting masses, disk properties, chemical compositions, stellar environments, migration histories, and gravitational encounters. A small change early in the process can eventually produce a very different mature system. That makes every planetary system useful, including our own. The solar system shows one way to arrange rocky planets and distant giants. Kepler 11 shows how tightly several planets can be packed near one star. TRAPPIST-1 shows 7 Earth-sized worlds confined to a remarkably compact region around a tiny ultra-cool star. 55 Cancri gives us 5 known planets distributed through a system containing an extremely close super-Earth. HR 8799 lets us directly observe 4 giant planets far from a young star, with each world slowly changing position over years of observations. None is simply a larger or smaller copy of another. They are different solutions to the same general problem. Take a forming star, surround it with rotating material, allow gravity and time to work, and see what remains. For everything we have considered so far, though, there has been one convenient assumption. There is one main star controlling the planetary orbits. Even when the system is crowded with worlds, the central gravitational arrangement remains relatively easy to picture. Put several planets around one star, and the details can become complicated. But every planet still has the same obvious sun at the center of the system. Remove that assumption and the geometry changes immediately. We already know that binary and multiple stars are common, and protoplanetary material does not simply refuse to form because a second star happens to be nearby. Planets can form in those environments too. Some stay close to one member of a stellar pair, while another sun moves farther away. Others take the more unusual route and circle 2 stars at once, placing both suns inside the planet's orbit. A planet moving around 2 stars at once sounds as though someone has made the orbital diagram unnecessarily difficult, but it is a real and increasingly well-studied type of planetary system. Astronomers call such a world a circumbinary planet. The word simply means that the planet travels around a binary star rather than around one individual star. The 2 stars orbit their shared barycenter on a relatively tight inner orbit, while the planet follows a much wider path around both of them. From far enough away, the planet responds mainly to the combined gravitational influence of the pair. That distance is important. If you place the planet too close to the binary, the changing gravitational pulls of the individual stars can make its orbit unstable. The planet may be pushed into a more eccentric orbit, thrown farther outward, sent inward toward one of the stars, or eventually ejected from the system. Stable circumbinary planets therefore generally need to remain outside a critical region around the stellar pair. Exactly where that boundary lies depends on the masses of the stars, how far apart they are, and how eccentric their orbit is. Numerical studies show that stable planetary regions can exist both close to one member of a wide binary and farther out around a binary as a whole. This gives planets in binary systems 2 basic ways to organize themselves. A planet can orbit one star while the second star remains farther away. Astronomers often call this an S-type orbit. The letter can be remembered as meaning the planet behaves rather like a satellite of one stellar component, although the terminology is simply conventional. The other possibility is a P-type orbit, where the planet circles the entire binary. That is the circumbinary arrangement. A planet in a P-type orbit does not travel around one star and then the other in some complicated figure 8 pattern. Figure 8 arrangements are not normally stable planetary orbits. Instead, the 2 stars remain inside the planet's much larger path and continue orbiting one another while the planet circles the pair. If you could watch the system from above, it would look like a small binary orbit turning rapidly inside a much larger planetary orbit. From the surface of a hypothetical moon around such a planet, the sky would be considerably less tidy. Both stars would move relative to each other. Depending on the geometry, they might appear close together at some times and farther apart at others. One could pass in front of the other. The combined amount of light reaching the planet could vary as the stars move through their orbit. Sunrise would no longer be a simple matter of one star appearing over the horizon. You might get one sunrise followed by another, or 2 suns rising close together, or one sun already above the horizon while the other catches up later. Calendar manufacturers would have several additional meetings. The system that turned this idea from a familiar science fiction image into an unambiguous astronomical observation was Kepler-16. Kepler-16 is also catalogued as KIC126444769, TIC2990963555, and Gaia DR 32133476355197071616. It contains 2 stars and the circumbinary planet Kepler 16b. The stars orbit each other every 41 days, while Kepler 16b completes its much wider orbit in about 229 days. The larger star has roughly 69% of the Sun's mass, and the smaller one about 20%. Kepler 16b itself is a gas giant roughly comparable to Saturn. Its announcement in 2011 attracted enormous attention because it provided the first unambiguous detection of a planet orbiting 2 stars. The comparison with Tatooine was immediate. There is, however, an important difference between Kepler 16b and the famous fictional desert planet. Kepler 16b is a gas giant. There is no known solid desert surface where someone can stand dramatically while looking at 2 sunsets. You would need a moon, and probably a very good coat, because Kepler 16b is much colder than Tatooine was usually portrayed. Its stars are both less luminous than the Sun, so even though the planet's orbital distance is not enormous by solar system standards, it receives considerably less heat. NASA describes its 229-day year and Saturn-like nature, while noting that the 2 stars would indeed provide the basic 2-sun view. Kepler 16 also shows why circumbinary planets can be surprisingly useful to astronomers. The system is oriented so that the stars eclipse one another from our viewpoint. Then the planet crosses in front as well. The timing of these events gives astronomers a large amount of information. When one star passes in front of the other, the total brightness changes. When the planet passes in front of one star, another dip appears. Because the stars themselves are moving, the planet does not transit a stationary target. Sometimes the star is moving toward the place where the planet crosses. Sometimes it is moving away. The intervals between planetary transits therefore do not have to be perfectly regular in the way they often are for planets around single stars. This irregularity initially sounds inconvenient. It is actually evidence. The changing transit timing tells astronomers that the planet is crossing a moving binary rather than a single central star. If every event occurred with suspiciously perfect regularity, the system would be easier to schedule but less informative. A second important circumbinary system is Kepler 34, catalogued as KIC 8572936, TIC 272369124, KOI-2459, and Gaia DR 32079692. 678778277712. Kepler 34 consists of 2 stars broadly similar in mass to the Sun and the circumbinary gas giant Kepler 34b. The planet takes about 288.8 days to complete one orbit around the binary. Kepler 34 is particularly useful because its 2 stars are more similar to each other than the pair in Kepler 16. Instead of one clearly dominant star accompanied by a much smaller red dwarf, the system contains 2 substantial stars moving around their common barycenter. Their stellar orbit is also noticeably eccentric. That means the distance between the stars changes throughout each orbit. At one point they are closer together, later they are farther apart. The gravitational field experienced by material around them is therefore not simply rotating at a fixed separation. A planet forming around such a binary has to develop inside a disk being influenced by 2 substantial moving masses on a non-circular orbit. And yet Kepler 34b exists. That fact matters because it demonstrates that planet formation is not restricted to binaries with one dominant star and a tiny companion. Circumbinary planets can emerge around more balanced pairs as well. A related system, Kepler 35, is catalogued as KIC 9837578 and KOY 2937. Its 2 stars are both somewhat less massive than the Sun and orbit each other in roughly 21 days. Kepler 35b, a Saturn-sized planet, circles the pair in approximately 131 days. NASA describes the two stellar components as smaller and cooler than the Sun and confirms the planet's circumbinary orbit. Kepler-35 helps reveal a pattern that became noticeable as more circumbinary planets were discovered. Many of the planets found by Kepler orbit not enormously far beyond the region where long-term stability becomes possible. They are not sitting almost on top of the stars, but they are often relatively close to the inner edge of the stable circumbinary zone. This may be connected with how planets migrate through circumbinary disks. A young planet can form farther outward and then move inward through interactions with surrounding gas. Eventually, the changing gravitational effects of the binary and the structure of the disk can slow or stop that inward migration. The planet may become parked near the edge of the unstable central region. That does not mean every circumbinary planet must end up there. Other configurations are possible, and observational biases matter because planets with shorter periods are easier to detect through repeated transits. Still, the orbital locations of known circumbinary planets have given astronomers useful tests for models of how planets move through disks around binary stars. The disk itself is different from the one that formed our solar system. Around one young star, a protoplanetary disk can extend inward until magnetic, thermal, and other processes begin clearing material close to the stellar surface. Around a close binary, the stars continually disturb the central region. Their gravity can open a cavity in the disk. Most of the planet-forming material then occupies a larger circumbinary disk outside the stars. Gas still moves, dust still collides, planetesimals can still form. But the central gravitational source is not one fixed mass. It is a rapidly moving pair. For a long time, astronomers wondered how difficult this would make the assembly of planets. The answer appears to be that it makes the process more complicated without preventing it. Simulations have shown that terrestrial planets can form in suitable circumbinary disks and survive for long periods when their orbits remain in dynamically stable regions. Then Kepler-47 made the situation even harder to dismiss as an occasional curiosity. Kepler-47 is catalogued as KIC 1002-0423, TIC 271-548206, KOI-3154, and Gaia DR 320805, 0652354, 09, 02912. Its central binary contains a Sun-like star and a much smaller companion that orbit each other every 7.45 days. Around them are three known circumbinary planets, Kepler-47b, Kepler-47d, and Kepler-47c. Their orbital periods are approximately 49, 187, and 303 days. This is not merely one planet managing to survive around two stars. It is an entire planetary system built around a binary. The innermost known planet is about 3 times Earth's radius. The middle planet is considerably larger, while the outer planet is between the sizes of Earth and Neptune. The whole arrangement is compact enough that the 3 planetary orbits would fit inside Earth's orbit if transferred directly to our solar system. That changes the question. Instead of asking, can a binary star have a planet? We have to ask the much broader question, what kinds of planetary architectures can binaries produce? Apparently more than one. Planets can share the same circumbinary disk, interact gravitationally, migrate, and settle into several stable orbits. Kepler-47 also helps separate the effects of planet formation from the architecture of our solar system. Our planets developed around one star. Kepler-47s formed around a moving pair, yet both environments produce multiple surviving worlds. The process does not require a single stellar center. It requires stable regions where material can remain long enough to assemble. The same physics is operating, but the geometry is different. TOI 1338 gives us another variation and demonstrates how new emissions have continued the search. The system is also known as EBLMJ 0608-5944 and carries the catalogue designation TIC 260128333. Its two stars orbit each other every 14.6 days. The larger star is slightly more massive than the Sun, while the second is a much smaller star. TOI-1338b, discovered with NASA's TESS mission, circles both stars in about 95 days and has a radius between that of Neptune and Saturn. Its transits behave exactly as we should expect in a circumbinary system. They do not arrive with the simple clockwork regularity of a planet crossing one's stationary stellar disk. NASA reported intervals of roughly 93 to 95 days between observed transits, with changing durations and depths because the stars move substantially between crossings. Imagine trying to catch a train whose station is also orbiting something else. The train can be perfectly regular. The station is the problem. TOI-1338 became more interesting when astronomers found evidence for a second planet, now listed in the NASA Exoplanet Archive as TOI-1338c. Unlike the inner planet, the second world was detected through radial velocity measurements rather than transits. The archive lists TOI-1338b and TOI-1338c as two confirmed planets in the system, with the outer planet taking roughly 216 days to orbit. This is important observationally because circumbinary planets are especially easy to miss if we depend only on transits. The orbital plane of a planet can slowly precess, meaning its orientation changes over time. A planet that crosses the stars from our viewpoint today may stop doing so later. TOI-1338b provides a good example. NASA noted that its changing orbital orientation would cause its observable transits to disappear for a period before returning years later. The planet does not disappear, only the alignment does. This means a binary system could contain planets that never transit during the years we happen to observe it. Radial velocity measurements give astronomers another way to detect them by looking for the gravitational effect of the planet on the stars. Even that is more difficult than ordinary radial velocity work because the two stars are already moving rapidly around each other. Researchers have to separate the large stellar binary signal from the much smaller effect produced by the planet. It is the astronomical equivalent of trying to notice a gentle wobble while standing on a merry-go-round. Kepler-64 takes us from two-star planetary systems into something larger. Kepler-64 is also known as PH1 and is associated with the catalogue designation KIC 4862625. The planet Kepler-64b, originally called PH1b, was identified through the Planet Hunters Citizen Science Project using Kepler data. It orbits a close pair of stars roughly every 137 days. Far beyond that inner system lies another binary pair, making the complete arrangement a four-star system. So the planet circles two stars directly, while another two stars belong to the wider system. Four suns exist in the same gravitational family, but the planet does not weave among all four. Hierarchy saves the arrangement again. The host binary occupies the center of the planet's orbit. The second binary remains extremely distant, roughly hundreds of astronomical units away. At the scale of the planet's year, that outer pair is more like a distant stellar companion than an equal participant in every orbit. This distinction is useful because the phrase, planet in a four-star system, can sound as though four stars are circling overhead every morning. Not necessarily. A planet's immediate sky depends on which part of the hierarchy it occupies. On Kepler-64b, the close inner pair would dominate. The remote binary would appear much farther away. The complete stellar system contains four stars, but the planet's local orbital problem is mainly circumbinary. NASA described PH1 as the first reported planet orbiting a double star that is itself orbited by another distant stellar pair. Other multiple star systems take the opposite approach. A planet can orbit one individual star inside a larger triple or quadruple system. Proxima Centauri provides the nearest familiar example. Proxima is also Alpha Centauri c, GJ 551, and HIP 70890. It is the distant third stellar member of the Alpha Centauri system, while Alpha Centauri A and B form the much closer binary pair. Proxima hosts confirmed planet Proxima Centauri B, so the planet belongs to a triple star system even though it orbits only one of those stars directly. Simbad identifies Proxima as GJ 551 and HIP 70890, while NASA identifies it as part of the Alpha Centauri triple system. From the point of view of Proxima B, Proxima is the local sun. Alpha Centauri A and B are distant stellar companions. Their gravity matters over large scales, but the planet does not circle all three stars each year. This is an S-type planetary orbit inside a larger multiple star hierarchy, rather than a P-type circumbinary orbit. The contrast with Kepler-64 is useful. In Kepler-64, the known planet travels around the inner two stars. In the Alpha Centauri system, Proxima's planet travels around only one member, while the other two remain much farther away. Both are planets in multiple star systems. Their orbital arrangements are completely different. This also affects what a planet's climate might experience. For a circumbinary world, both central stars can contribute substantially to the incoming radiation. As the stars move around each other, their individual distances from the planet change. One may eclipse the other. The amount and colour of starlight can vary. If the two stars have different temperatures, the spectrum reaching the planet also changes slightly as their positions change. That does not necessarily produce violent climatic swings. A circumbinary planet usually orbits much farther out than the star's separation, so the changes in total distance may be relatively modest. An atmosphere and ocean can also smooth short-term variations in heating. Still, the illumination pattern is more complicated than Earth's. A planet orbiting one member of a wide binary experiences something else. Its host star provides most of the normal daylight. The distant stellar companion could appear as an extremely bright star in the sky, depending on its distance and luminosity. It may add little to the planet's surface temperature while still producing a spectacular nighttime object. Move the binary stars closer, and the companion contributes more light, but it also creates stronger gravitational restrictions on where stable planets can orbit. Habitability in these systems therefore cannot be summarized by drawing one simple ring around one star. Astronomers have to consider the combined radiation from multiple stars and the long-term stability of the orbit. A location may receive a suitable average amount of energy, but be dynamically unstable. Or the orbit may be perfectly stable while the combined stellar heating is too strong. The habitable region and the stable region have to overlap. There is also the question of how a circumbinary planet forms in the first place. The discoveries we have just looked at tell us that it happens. They do not automatically tell us exactly where each planet assembled. A close binary can clear the inner portion of its surrounding disk. Material farther out can still collide and grow. Planetary embryos can form. Larger planets can then migrate inward until interactions with the binary and disk alter that migration. Some worlds may stop near the inner edge, others may remain farther out. Several may form and interact with one another, a system such as Kepler-47 and TOI 1338 demonstrate. Kepler-16 adds another clue because the stellar and planetary orbital planes are closely aligned. The original discovery work found that the three bodies move within a very small range of a common plane, consistent with formation from a shared circumbinary disk, rather than a planet being randomly captured much later. That shared plane is what we would expect from a flattened rotating disk. The binary forms near the middle. The remaining gas and dust rotate around it. Planets develop from that material. The result can look complicated today, but it may have begun from one coherent rotating structure. The same principle applies to wider multiple star systems, although fragmentation can create several separate disks. A young binary may have a disk around each individual star and another large disk around both. Triple systems can contain tilted disks associated with different components. By the time we see a mature planetary system, most of the construction work has already happened. The star has settled into a relatively stable phase. Much of the original gas has disappeared. the surviving planets have established recognizable orbits, and the violent collisions and migrations of the earliest period have usually slowed down. To understand why one system ends up with a hot Jupiter, another with 7 tightly packed rocky worlds, and another with planets circling 2 suns, we have to look much earlier. Stars are not born as small glowing versions of adult stars. They begin inside enormous clouds of cold gas and dust known as molecular clouds. These clouds are composed mainly of molecular hydrogen, along with helium and much smaller amounts of heavier elements and dust grains. They can extend across many light years and contain enough material to produce hundreds or thousands of stars. Most of the cloud does not collapse at once. Certain regions become denser than their surroundings. A disturbance may compress part of the cloud. Turbulence can create concentrations of material. Expanding shells from nearby massive stars can push gas together. Gravity then begins pulling material inward. Once a dense region becomes sufficiently massive, gravity can overcome the internal pressure trying to keep it spread out. Collapse begins. At first, there is no clearly defined star in the middle. There is simply a region becoming denser, hotter, and more compact. As the material falls inward, conservation of angular momentum becomes increasingly important. Even if the original cloud was rotating only slightly, shrinking it causes the rotation to speed up. You can see the same basic effect when an ice skater pulls their arms inward and begins spinning faster, although a collapsing molecular cloud performs the demonstration on a slightly less convenient scale. The incoming material cannot all fall directly into the center. Instead, much of it settles into a flattened rotating structure. A dense object develops in the middle. A disk develops around it. This central object is the protostar. It is not yet a normal main sequence star like the Sun. A mature star such as the Sun produces most of its energy through nuclear fusion in its core, where hydrogen nuclei combine into helium. A protostar has not yet reached that stable condition. It is being heated mainly by gravitational contraction and by material continuing to fall onto it. As gas descends deeper into the protostar's gravitational field, gravitational potential energy is converted into heat. The young object can therefore become bright even before stable hydrogen fusion begins in its core, and it is rarely sitting in a clean empty region. It may still be surrounded by an envelope of infalling gas. A thick disk can hide it at visible wavelengths. Material may be falling inward while other material is being launched outward in narrow jets. Young stellar systems are less like finished solar systems and more like construction sites where several processes are happening at once. One of the best known real examples is HL Tauri, usually shortened to HL Tau. HL Tau is a young star in the Taurus star-forming region, about 450 light-years from Earth. It is also identified in catalogues including 2 MAS SJ 04-31384, 3+1813576, and Gaia DR 334-09218, 4-695-4905-3184. Astronomers have studied it for decades, but it became especially famous after the Atacama Large Millimeter/Submillimeter Array, or ALMA, produced an extraordinarily detailed image of the material around it. Instead of showing a smooth disk, the observations revealed a series of bright rings separated by dark gaps. That was surprising because HL Tau is extremely young, roughly around 1 million years old, yet its disk already contains complex structure. ALMA observations made the system one of the best-known examples of how quickly planet-forming disks can become organized. Those rings and gaps immediately raised an obvious possibility. Planets might already be forming inside the disk. A growing planet gravitationally interacts with nearby gas and dust. If it becomes massive enough, it can disturb material around its orbit and contribute to the formation of gaps and rings. Later analysis of HL Tau found gaps in gas that corresponded with some of the gaps seen in dust, strengthening the idea that young planetary bodies could be affecting the disk. Researchers are still careful about assuming that every ring in every disk must be produced by a planet, because other physical processes can also create structure, but systems such as HL Tau showed that planet formation may begin remarkably early. This changes the old mental picture of star formation. It is tempting to imagine a sequence where the star finishes forming first, waits for things to calm down, and only then allows planets to begin assembling. Nature does not appear to be that organized. Star formation and planet formation overlap. While the central star is still young and changing, dust grains in the surrounding disk are already colliding. Tiny particles stick together. They grow into larger grains. Grains become pebbles. Pebbles can concentrate in particular regions of the disk. Eventually, larger solid bodies known as planetesimals may form. From those planetesimals, planetary embryos can develop. By the time the central star is approaching its stable main sequence life, the surrounding planetary system may already be well underway. This early overlap is one reason astronomers care so much about protoplanetary disks. They are not simply leftover material. They are the environment in which planets are built, and the disk does not remain available forever. Young stars produce radiation, winds, and magnetic activity that gradually remove gas. Nearby massive stars can also irradiate disks and accelerate their dispersal. After several million years, much of the gas in a typical protoplanetary disk has usually disappeared. That gives giant planets a deadline. A rocky planet can continue growing through collisions between solid bodies after most of the gas is gone. A Jupiter-like planet cannot wait indefinitely. If it is going to gather a massive envelope of hydrogen and helium, it must do so while the disk still contains large amounts of gas. Planet formation therefore includes a race that nobody involved is aware of. Build a sufficiently massive core before the gas disappears. If you manage it, you may become a gas giant. If not, you may remain a smaller rocky or icy world. The exact process is more complicated than that simple description, and astronomers continue debating how different giant planets form. But the limited lifetime of the gas disk is a central part of the problem. Another nearby young star helps astronomers study a somewhat later stage. TW Hydrae, also catalogued as HIP 53911, Tier C7208-347-1, 2MAS-SJ 11015191-344217, Core and Gaia DR 354-017956625-5605-00352, is a T Tauri star surrounded by a nearly face-on protoplanetary disk. NASA observations describe the system as a T Tauri star with a disk, while detailed imaging has revealed structure within the material surrounding it. The nearly face-on orientation is useful. If a disk is turned edge-on, we see its narrow side, and some of the central regions can be hidden by dust. Looking almost directly down onto a disk is more like looking at a plate from above. Rings, gaps, spirals, and other structures are easier to map. TW Hydrae is relatively close to us by star formation standards, which makes it particularly valuable for high-resolution observations. And even a disk that looks calm in an image is not stationary. Gas orbits the star. Dust drifts. Particles collide. Different-sized grains respond differently to gas pressure. Material can move inward. Some regions accumulate solids more efficiently than others. Magnetic fields interact with ionized gas. Potential planets disturb the disk through gravity. The finished image may look like a neat set of rings, but the physical system is active. One of the reasons rings matter is that planet formation has a serious growth problem. Small dust grains can stick together relatively easily. Eventually, however, larger particles encounter barriers. Collisions may become violent enough to break objects apart rather than combine them. Gas drag can cause solid material to move inward toward the star. If everything simply spiraled inward too quickly, building large planets would become difficult. Dense rings can help. They may act as regions where solid particles accumulate, giving them more time and material to grow. Large surveys with ALMA have shown that rings, gaps, arcs, and spirals are common in protoplanetary disks rather than being a peculiarity of HL Tau. The young star does not behave calmly either. Stars in this stage are often called T Tauri stars when they are low-mass young stars similar in a ventral scale to the Sun. The class is named after T Tauri itself. T Tauri is catalogued as HD284419 HIP2 039 O and 2MASS J 0421593 plus 1 932063. Among many other identifiers, the object that gave its name to the entire class is itself part of a complicated young multiple star system. That is appropriate, because star formation often produces more than one star. The same collapsing cloud that creates one protostar can fragment. Several dense centers can form. Those protostars may end up gravitationally bound. Some become binaries, others become triples or larger systems. Some young stars begin in loose groups that later separate. This connects directly with the multiple star systems we looked at earlier. A binary does not suddenly appear after two fully grown stars happen to notice one another. In many cases, the relationship begins while the objects are still forming. Their surrounding disks can interact from the beginning. A binary might possess a disk around each individual protostar as well as a larger circumbinary disk around both. In a triple system, the geometry can become even more complicated. Disks may be tilted relative to one another. A companion can truncate a disk, limiting how far it extends. Spiral structures can develop. Material can move between different parts of the system. Some young companions may even alter each other's growth rates. The eventual masses and orbits of the stars are influenced by what happens during this early period. The same is true for their planets. A planet forming around one member of a binary is developing in an environment that may already be shaped by the second star. A circumbinary planet begins inside material orbiting both stars. The mature planetary arrangements we discussed earlier are therefore consequences of conditions established very early. To see an even clearer case of planet formation happening in real time, astronomers can look at PDS-70. PDS-70 is also known as CD-408434 and appears in catalogues as 2MASS J14081 015-41235525 and Gaia DR3611 01415633096130056. It is a young K-type T Tauri star, roughly 370 light-years away. More importantly, PDS-70 is surrounded by a protoplanetary disk and hosts two directly imaged giant planets, PDS-70b and PDS-70c. NASA describes the star as roughly 5 million years old, with both young giant planets still gaining material from the surrounding disk. This is a particularly valuable system, because astronomers are not merely inferring that planets might be forming from gaps in the disk. They can observe the planets themselves. PDS-70b was directly imaged inside the disk. PDS-70c was later identified farther out. Material continues falling onto the young planets. Observations indicate that PDS-70c possesses a circumplanetary disk, meaning a disk of material around the planet itself. That introduces another level of formation. A star has a disk. Inside that disk, a planet forms. Around the forming planet, another smaller disk can develop. Moons may eventually form from such circumplanetary disks. Jupiter's large Galilean moons are thought to have formed from material in a disk around the young Jupiter. So when astronomers observe a circumplanetary disk around an object such as PDS-70c, they may be looking at the kind of environment where a future moon system could assemble. A planetary system can therefore reproduce the same general disk structure at multiple scales. The molecular cloud feeds the young star. The stellar disk feeds planets. A planetary disk can feed moons. Gravity does seem fond of reusing a successful design. PDS-70 has also given astronomers information about water. Observations with the James Webb Space Telescope detected water vapor in the inner region of the system's protoplanetary disk. inside the large gap where the giant planets orbit farther out. That matters because water is a major ingredient in planetary chemistry. Where water exists as vapour and where it freezes onto grains depends on temperature. This creates what astronomers call the water snowline. Inside the snowline, temperatures are generally high enough that water tends to remain gaseous. Beyond it, water can freeze onto dust grains. That change affects how much solid material is available for building planets. Ice adds mass to grains and planetesimals, potentially helping the cores of giant planets grow more rapidly in colder outer regions. The location of the snowline is not fixed throughout a star's youth. Young stars change. Their brightness can vary. Material falls onto them in bursts. A sudden rise in luminosity can heat the disk and move the snowline outward. V883 Orionis provides an unusually clear example. V883 Orionis, also listed as 2MASSJ 0538181 0-07022259 and Gaia DR3301610690 092103766704, is a young variable object in Orion. It experienced a major increase in brightness associated with enhanced accretion. That outburst heated the disk enough to push its water snowline outward to around 40 astronomical units, making the transition possible to resolve with ALMA. 40 astronomical units is roughly comparable to the scale of Pluto's orbit around the Sun. Under ordinary conditions around a young Sun-like star, the water snowline would usually lie much closer to the star. The outburst temporarily moved it outward by a large amount. This shows that protoplanetary disks are not thermally fixed environments. The conditions experienced by growing planets can change as the central star changes. A planetesimal might form in a region where water is frozen. Later, heating alters the local chemistry. Then the star dims again. Material moves. Different compounds condense at different temperatures. The composition of a forming planet therefore depends partly on where it formed, and partly on what happened around it while it was forming. That connection between location and chemistry is one reason astronomers analyse molecules in young disks. They're trying to understand not only where planets appear, but what those planets are made from. Carbon monoxide, water, simple organic molecules, silicates, and many other substances can be traced at different wavelengths. The final atmosphere and bulk composition of a planet can preserve some of that chemical history. Not perfectly, because later impacts, volcanic activity, atmospheric loss, and internal processing can change things substantially. But the disk provides the starting inventory. Young systems also produce some of the most visible signs of star formation: jets. A protostar surrounded by an accretion disk may eject narrow streams of material along its rotational axis. The exact physics involves magnetic fields interacting with the rotating disk and young star. Material falling inward does not all remain in the system. Some is redirected outward at high speed. These jets can extend for enormous distances compared with the size of the star. When they slam into surrounding gas, they produce glowing structures known as Herbig-Haro objects. This can seem slightly contradictory. The protostar is trying to gain mass, yet it is simultaneously throwing some material away. The outflows actually help the system evolve by carrying away angular momentum. If everything kept too much angular momentum, material would have difficulty moving inward. By removing some angular momentum, jets and winds allow other material to continue accreting onto the star. Star formation therefore involves both gaining and losing matter at the same time. Apparently even a newborn star has administrative overhead. The amount of material a protostar receives is not necessarily constant either. Accretion can occur unevenly. Some young stars experience bursts where the rate of infalling material increases dramatically. These events cause the star to brighten. V883 Orionis is one example of an accretion outburst. Fu Orionis, the prototype of another class of young eruptive stars, provides another. During such events, the luminosity increase can heat large sections of the disk. That may alter ice, chemistry, dust structure, and potentially the conditions experienced by forming planets. The young system is therefore not a quiet disk, slowly building worlds at a fixed temperature. It can experience episodes. The central star changes, the disk responds, the planets continue growing inside that changing environment. Eventually, however, the supply of material begins to run out. The original envelope around the protostar thins, accretion rates decrease, jets weaken. The star contracts toward the main sequence. Its core becomes hot and dense enough for stable hydrogen fusion. At that point, the object begins the long phase we normally think of when we picture a star. For a star with roughly the Sun's mass, the transition from collapsing cloud to a stable main sequence object takes tens of millions of years. More massive stars form more quickly. Lower mass objects can take longer. The surrounding disk evolves on its own schedule and often disappears before the star is completely settled. This means the early planetary system may still be rearranging itself after the obvious protoplanetary disk is gone. Rocky planetary embryos can continue colliding. Giant planets may scatter smaller bodies. Asteroid belts are reshaped. Comets are moved into distant reservoirs or thrown out. Moons continue forming and migrating. Some planets collide catastrophically. Others settle into stable resonances. The transition from young stellar system to mature planetary system is gradual rather than a single moment. There is no morning when the star wakes up, checks the disk and announces that construction is complete. Our own solar system preserves evidence of this early period. Meteorites contain some of the oldest solid material available for study. Their ages point to the solar system forming about 4.6 billion years ago. The planets were not immediately in their current forms. Earth grew through repeated collisions. The Moon probably formed after a major impact involving the young Earth and another planetary body. The giant planets may have migrated. Large numbers of planetesimals were scattered. Some became asteroids, some became comets. Some struck the young planets. Others were expelled into interstellar space. If we could observe the solar system during its first few million years from a distant telescope, it might look much more like one of the young systems we study today. A disk surrounding a young sun. Bright rings of dust, gaps developing, planets still gathering material, collisions, changing orbits. Perhaps the young Jupiter influencing the disk before Earth had finished assembling. That is what makes objects such as HL Tau, TW Hydrae, V883 Orionis, T Tauri, and PDS 70 so valuable. They are not earlier versions of the solar system in a strict sense. Their stars have different masses and environments. Their disks contain different amounts of material. Their companions and planets may follow entirely different histories. But they allow astronomers to observe stages that our own system passed through billions of years ago. HL Tau shows an extremely young disk already divided into rings and gaps. TW Hydrae provides a nearby view of an evolved protoplanetary disk around a T Tauri star. V883 Orionis shows how a burst in stellar accretion can alter disk temperature and move the water snowline. PDS 70 allows astronomers to study giant planets that are still growing inside the disk from which they formed. Taken together, systems like these show that the categories we have been using are connected by time. A young protostellar system can become a single-star planetary system. Another can become a binary with circumbinary planets. A collapsing cloud can produce a triple star. A disk can produce several planets, or perhaps very few. Some worlds remain near their birth locations. Others move dramatically before the system settles. What we call a star system type is therefore partly about architecture and partly about when we happen to observe it. A system at 1 million years old may be classified by its protostar and disk. At 100 million years, we may describe it by its planets. Billions of years later, the same system can change category again, because stars themselves do not remain young forever. Once stable hydrogen fusion begins, a star can spend a very long time in what seems like an almost unchanging state. For the Sun, that period lasts billions of years. For a small red dwarf, it can last vastly longer. For a massive star, it may be surprisingly brief. The important point is that the material being assembled in these young systems is building arrangements that eventually have to survive the entire lives of their stars. Some will not. A planet may remain in orbit while its star slowly brightens. A binary may exchange matter when one member expands. A planetary system may be radically altered when its central star becomes a giant. The same star we have just watched being assembled from gas can eventually shed its outer layers or explode. A quiet young object, such as the ones hidden inside today's molecular clouds, is therefore only the first recognizable version of something that may look completely different billions of years later. The systems we have followed so far have mostly contained stars in recognizable stages of ordinary stellar life. They form, gather planets, settle onto the main sequence, and spend millions or billions of years producing energy through nuclear fusion. But a star does not remain in that state forever. Eventually, the available fuel in its core changes. The internal balance between gravity pulling inward and pressure pushing outward changes with it. What happens next depends mainly on the star's mass, and the result can be one of several compact stellar remnants, a white dwarf, a neutron star, or a black hole. These objects are not simply smaller versions of normal stars. Their densities are extreme. Their gravitational fields can be enormous. Some rotate hundreds of times every second. Some strip gas from nearby companion stars. Some continue hosting planets. Others reveal themselves almost entirely through what their gravity does to something else. And because many stars begin life in binary or multiple systems, stellar death does not necessarily destroy the system. Sometimes it simply replaces one of the members. A pair that begins as two ordinary stars might later contain one ordinary star and one white dwarf. Given enough time, both stars might become white dwarfs. A massive binary can produce a neutron star alongside a normal companion. Another can eventually contain two neutron stars. In still more massive systems, one member may collapse into a black hole, while the second continues shining nearby. The gravitational partnership can survive even though one participant has changed almost beyond recognition. The least violent of the major stellar remnant paths produces a white dwarf. A star broadly similar in mass to the Sun does not have enough mass for its core to continue fusing heavier and heavier elements, all the way toward the conditions that produce a core collapse supernova. Instead, after spending its main life fusing hydrogen and then evolving through later stages, it expands into a giant. The outer layers are eventually lost. What remains is the exposed stellar core. That core becomes a white dwarf. A typical white dwarf is roughly comparable to Earth in size while containing a substantial fraction of a star's mass. It no longer generates significant new energy through ordinary core fusion. It begins extremely hot and then cools gradually over billions of years. NASA describes white dwarfs as Earth-sized stellar remnants, left after stars like the Sun shed their outer layers. The strange thing is, what prevents the white dwarf from collapsing farther? In an ordinary star, heat generated by fusion helps maintain pressure against gravity. In a white dwarf, fusion is no longer providing that support in the same way. Instead, quantum mechanics becomes essential. Electrons cannot simply be forced into identical states without limit. As matter is compressed, this creates what is called electron degeneracy pressure. You do not need to imagine the electrons deliberately resisting gravity. They have not formed a committee. It is a consequence of the rules governing matter at extremely high density. Electron degeneracy pressure allows a white dwarf to remain stable, as long as its mass stays below the relevant upper limit. That gives us one of the closest and best-known stellar remnant systems, Sirius. We encountered Sirius earlier as a binary, but now the smaller member becomes the interesting one. Sirius A is the brilliant normal star that makes Sirius the brightest star in Earth's night sky. Its companion, Sirius B, is a white dwarf. Sirius B is also catalogued as Alpha Canis Majoris B, HD 48915b, GJ244b, WD0642-166, and Gaia DR3 2947 05046653187324. The two stars orbit each other approximately every 50 years. Hubble observations show Sirius B as a tiny faint point beside the overwhelmingly brighter Sirius A. Sirius B is only around the size of Earth, yet it contains roughly a star's worth of material compressed into that volume. If you could somehow bring a small amount of white dwarf matter to Earth without immediately creating several practical difficulties, it would be enormously dense compared with ordinary material. The important part for the system is that Sirius B did not begin as a white dwarf. It was once a normal star. In fact, the star that produced Sirius B must originally have been more massive than Sirius A, because it evolved faster. It completed its ordinary stellar evolution, expanded, lost its outer material, and left behind the white dwarf we see now. Sirius A is still shining normally beside it, so when we observe the pair today, we are seeing two different points in stellar evolution within the same system. One member has already reached the compact remnant stage, the other has not. Given enough time, Sirius A will evolve as well. This is a useful reminder that a stellar system's type can change without the gravitational relationship disappearing. A system can spend hundreds of millions of years as a pair of ordinary stars and then spend billions more as a normal star paired with a white dwarf. Some white dwarfs keep planets too. One of the most remarkable examples is WD 1856 plus 534. The star's name is already a catalogue designation, and its planetary companion is called WD 1856 plus 534b, often shortened to WD 1856b. NASA's Exoplanet Archive lists the white dwarf with the confirmed giant planet orbiting it approximately every 1.4 days. The system also has distant stellar companions, the red dwarfs G229-2 OA and G229-20b. WD 1856b is approximately Jupiter-sized, while the white dwarf it circles is roughly Earth-sized. That creates a very strange visual comparison. The planet is physically much larger across than the star it orbits. Usually planets crossing stars during transits block a very small fraction of the stellar surface. Here the planet can cover a huge portion of the white dwarf from our viewpoint. The difficult question is how the planet reached its current orbit. It travels extremely close to the white dwarf. But before becoming a white dwarf, the original star expanded dramatically into a red giant. A planet orbiting at the present distance would not have survived comfortably in that location. Recent Webb observations have continued investigating how WD 1856b survived and migrated into its present tight orbit after the star's transformation. This tells us that planetary systems can continue evolving after stellar death. The creation of a white dwarf is not the end of orbital rearrangement. Planets farther out can survive. Their orbits can change as the star loses mass. Interactions among planets or with stellar companions can move objects inward or outward. Asteroids and comets can be disturbed. Some material can fall toward the white dwarf. Astronomers actually find heavy elements in the atmospheres of many white dwarfs that should otherwise settle rapidly below the visible surface. One explanation is that the stars are continually being polluted by planetary debris, such as disrupted asteroids. A white dwarf system can therefore contain something like the archaeological remains of its former planetary system. The planets may not occupy their original orbits. Some may have been engulfed. Others survived. Smaller bodies may have been scattered. Fragments may now form dusty disks around the stellar remnant. What looks like a quiet, fading white dwarf can still be gravitationally processing material left over from its earlier life. For more massive stars, the ending becomes much more violent. A sufficiently massive star continues fusing progressively heavier elements in its interior. Hydrogen gives way to helium. Later stages produce carbon, neon, oxygen, silicon, and eventually an iron-rich core. Iron changes the situation because fusing iron does not release energy in the useful way earlier fusion stages do. Once the core can no longer support itself, collapse proceeds extremely rapidly. The outer star can explode in a core collapse supernova. If the collapsed core remains within the right mass range, the remnant becomes a neutron star. NASA describes neutron stars as objects containing more than the Sun's mass compressed into a sphere only about 20 kilometers across. At those densities, ordinary atomic structure does not survive. Electrons and protons are forced together under immense pressure, producing matter dominated by neutrons. The resulting object is one of the densest forms of matter astronomers can observe directly. A neutron star is so compact that the difference between standing on its surface and hovering slightly above it would be a matter of survival only in the most theoretical sense. Its gravity is extreme, its magnetic field can be enormous, and because the original stellar core shrinks from something thousands of kilometers across to something roughly the size of a city, conservation of angular momentum can make the remnant rotate very rapidly. It is the same principle as the spinning skater pulling in their arms, only now the skater is a collapsed stellar core. Some neutron stars become pulsars. A pulsar is not a completely separate kind of object from a neutron star. It is an observational type of neutron star. A rotating neutron star with strong magnetic fields can produce beams of radiation near its magnetic poles. If one of those beams sweeps across Earth as the star rotates, telescopes detect a repeating pulse. The radiation is not necessarily switching on and off. The beam is rotating in and out of our line of sight. NASA compares this behavior to a lighthouse, and pulsars have been detected at radio, visible, X-ray and gamma-ray wavelengths. So every pulsar is a neutron star, but not every neutron star appears to us as a pulsar. The beam might never point toward Earth. The neutron star may have slowed down, its magnetic configuration may be different, or it may be easier to detect through X-rays, or another effect. One of the most famous pulsars is the Crab pulsar, PSRB 0531+21, also designated PSRJ 0534+2200. It sits near the centre of the Crab Nebula, the expanding debris from a supernova observed from Earth in the year 1054. The pulsar rotates about 30 times per second. What appears in ordinary images as a cloud of glowing material contains, near its centre, a city-sized neutron star spinning faster than a kitchen blender and driving energetic particles into its surroundings. That is already strange enough for one object. Then neutron stars begin joining systems. PS RB1257+12 provides one of the most unexpected examples. This millisecond pulsar hosts 3 confirmed planets, PS RB1257+12 B, C, and D. The 2 larger planets, C and D, were announced in 1992 and became the first confirmed exoplanets found around another star. The smaller inner planet was confirmed later. NASA's exoplanet archive lists orbital periods of about 25, 67, and 98 days. Think about how odd that discovery was. For generations, people imagined the first known planets beyond the solar system would probably be found around a quiet star resembling the Sun. Instead, some of the first confirmed worlds turned up around the collapsed remnant of an exploded massive star. PSR B1257+12 rotates extremely rapidly and produces precise pulses that function almost like a clock. The planets were found because their gravity causes tiny changes in the arrival times of those pulses. When the pulsar moves slightly toward Earth, pulses arrive slightly earlier. When planetary gravity moves it away, they arrive later. By measuring those timing changes, astronomers can detect very small orbiting bodies. Pulsar timing is so precise that planets far smaller than typical early radial velocity discoveries can be detected. The larger mystery is how such planets came to exist. Did some planetary material somehow survive the supernova? Did the planets form later from a disk of material created after the explosion? Were they assembled from debris associated with a companion star? Different scenarios have been explored because forming an ordinary planetary system before a massive star explodes and then leaving it unchanged afterward is not a particularly easy explanation. Whatever their exact history, the planets demonstrate that stellar remnants can possess organized planetary systems. Neutron stars can also orbit other neutron stars. PSR B1913+16, usually called the Hulse-Taylor binary pulsar, was discovered in 1974. The pulsar and its compact companion complete an orbit in only about 7.75 hours. By precisely timing the pulses over many years, astronomers measured the orbit shrinking exactly in the way expected if the system were losing energy through gravitational radiation. This was important because gravitational waves had not yet been detected directly. The changing orbit provided indirect evidence that the binary was radiating energy in the form predicted by Einstein's general relativity. A system containing two objects too small to see as ordinary stellar disks was telling astronomers about the structure of space-time through the timing of radio pulses. Then came an even more remarkable system, PSRJ 0737-3, 039A and PSRJ 0737-3039b form what is commonly called the double pulsar. Both objects are neutron stars. Both have been observed as pulsars. The system therefore lets astronomers track two rotating neutron stars orbiting one another in an extraordinarily relativistic environment. NASA's Jet Propulsion Laboratory described it as the first known binary system in which both neutron stars were detected as pulsars. The two objects continually affect one another. Their gravitational field alters the orbit. Their spin axes can slowly change direction. Radiation from one interacts with the environment around the other. General relativity produces measurable effects because the objects are massive, compact, and close. If the Sun and Earth are an excellent system for learning basic orbital mechanics, the double pulsar is what happens when nature decides the examination paper should be considerably harder. Over very long periods, binary neutron stars can spiral inward as they lose energy through gravitational waves. Eventually some merge. When that happens, the collision can create a burst of gravitational waves and electromagnetic radiation known as a kilonova. These mergers are important sites for the production of very heavy elements. A pair of stellar remnants can therefore spend millions or billions of years orbiting quietly enough that we detect them mainly through radio pulses, then finish with one of the most energetic events in the universe. Push stellar collapse farther, and a neutron star is no longer enough. If the collapsing core is sufficiently massive, no known pressure can halt the collapse at neutron star density. A stellar mass black hole forms. The defining feature of a black hole is the event horizon, a boundary beyond which escape becomes impossible. This includes light. That is why the object itself is black. But a black hole in a stellar system can be surprisingly easy to notice, because the material around it does not have to be dark at all. Gas falling toward a black hole can form an accretion disk. As material moves inward, friction and other processes heat it enormously. The disk can become a strong source of X-rays. Jets may be launched from the region around the black hole. The result is the slightly confusing situation where an object famous for allowing no light to escape from inside its horizon can sit inside one of the brightest high-energy systems in the sky. We are seeing the material outside the black hole. One of the best-known examples is Cygnus X1. Cygnus X1 is a binary containing a stellar mass black hole and a massive blue companion star commonly associated with HDE 226868. The black hole and star orbit each other in only a few days. Material flowing from the massive star is captured by the black hole's gravity, producing a hot X-ray emitting environment. NASA measurements placed the black hole at around 21 times the Sun's mass and the companion at roughly 40 solar masses. Cygnus X1 became historically important because it was one of the earlier strong cases for a stellar mass black hole. Astronomers could see the companion star. They could measure its orbital motion. Something massive was pulling on it. Yet the companion responsible for that gravitational influence did not behave like an ordinary luminous star. From the orbital measurements, the unseen object's mass was too high for a normal neutron star. The simplest explanation was a black hole. Again, gravity revealed something light could not show directly. The orbit becomes a scale. Measure how the visible star moves, estimate its mass, determine the orbital period and geometry, and you can constrain the mass of the unseen companion. This is similar in principle to detecting exoplanets through stellar motion. The difference is that instead of finding something with the mass of Jupiter, you may discover an invisible object containing several or tens of solar masses. Not every stellar black hole is actively consuming enough material to shine strongly in X-rays. That point has become increasingly important. For decades, the easiest stellar mass black holes to discover were the noisy ones. Find an X-ray source and identify a companion star, measure the orbit, determine whether the compact object is too massive to be a neutron star. This naturally biased discoveries toward interacting binaries. A quiet black hole with a normal star in a wide orbit could be much harder to find. Gaia BH1 demonstrates another approach. Gaia BH1 is also designated Gaia DR 34373465352415301632. It consists of a sun-like star orbiting an unseen stellar mass black hole. ESA reported that Gaia detected the system because the visible star's motion across the sky revealed the gravitational influence of the invisible companion. Gaia BH1 lies roughly 1,560 light-years away. This black hole is not announcing itself through a spectacular bright accretion disk like Cygnus X1. The system is comparatively quiet. The ordinary star moves. Gaia measures that motion extremely precisely. The orbit says that something massive is present. Additional observations fail to reveal the light expected from an ordinary stellar companion of that mass. A black hole provides the explanation. Systems such as Gaia BH. One suggests that the Milky Way may contain a large population of quiet stellar black holes that are difficult to detect simply because they are not currently feeding very much. A black hole does not automatically vacuum up everything nearby. This is one of the most persistent misunderstandings about them. At a large enough distance, orbiting a black hole is gravitationally similar to orbiting any other object with the same mass. If the Sun were somehow replaced instantly by a black hole, with exactly one solar mass, ignoring the fact that real stellar evolution cannot produce this situation, Earth's orbit would not suddenly collapse inward. We would have several other problems, particularly the loss of sunlight, but the gravitational orbit would remain essentially the same. Black holes become especially destructive when objects approach very closely, or when gas is available for accretion. That makes binary geometry crucial. A black hole can exist beside another star without continuously consuming it. If the stars are widely separated, the ordinary companion can continue its life with relatively little material transfer. Bring them close enough, however, and the situation changes. V404 Cygni, also known as GS 2023 plus 338, provides a famous example. It contains a stellar mass black hole orbiting with an evolved companion star. During active periods, gas transferred toward the black hole forms a hot accretion flow and produces enormous X-ray outbursts. NASA's SWIFT mission observed a major eruption in 2015, when the system became intensely variable across the electromagnetic spectrum. The black hole itself did not suddenly begin shining. The material around it did. Gas accumulated, conditions in the accretion disk changed. Material rushed inward at a much greater rate. The system brightened dramatically. Then the activity decreased again. This behavior gives us another important distinction between the remnant and the system containing it. A neutron star or black hole can remain fundamentally the same object, while the system's observable appearance changes enormously depending on how much material is reaching it. A quiet black hole binary may be faint. Increase the accretion rate, and the same basic system can become one of the brightest X-ray sources in the sky. White dwarfs can behave similarly in their own mass range. Place a white dwarf close enough to a normal companion, and material may begin flowing onto the white dwarf. That can produce dwarf novae, classical novae, and, under some circumstances involving white dwarfs, thermonuclear supernovae. A neutron star gaining gas from a companion can produce powerful X-rays and bursts. A black hole supplied with gas can create a luminous accretion disk and sometimes jets. The compact object's identity determines part of the behaviour. The companion star and orbital separation determine much of the rest. That is why stellar remnants cannot be understood by studying only the remnant. The system matters. Once matter begins crossing from one star to another, a binary system stops behaving like two separate stars that merely happen to share an orbit. The stars begin changing each other directly. That can happen when one member expands with age, when stellar winds carry material across the system, or when the orbit becomes tight enough that a star can no longer keep all of its outer atmosphere gravitationally to itself. Astronomers describe the region around each star where its gravity dominates as a Rochlube. In a detached binary, both stars fit comfortably inside their own Rochlubes, so little or no material passes directly between them. If one star expands until it fills its Roche lobe, however, gas can flow through the gravitational balance point between the stars and toward the companion. This is called Roche lobe overflow. The phrase sounds fairly calm. The physics often is not. The transferred material carries mass, energy, and angular momentum. It can alter the orbit. It can change the masses of both stars. It can create an accretion disk. It can cause eruptions, X-rays, ultraviolet radiation, jets, or thermonuclear explosions. Most importantly, it can make a star evolve in a way that would have been impossible if it had lived alone. Algol provides one of the classic examples. Algol, Beta Persei, is also catalogued as HD19356 and HIP14576. The complete system contains 3 stars, but the close inner pair, Algol A and Algol B, is responsible for its famous variability. From Earth, their orbit is aligned so that the stars regularly eclipse each other. When the fainter star crosses the brighter one, the total brightness drops noticeably. People noticed Algol's changing brightness long before anyone understood what was causing it. Modern observations revealed something even more interesting. Algol B is less massive than Algol A, yet it is much farther along in its stellar evolution. That seems backward. A star with greater mass generally burns through its fuel faster and evolves first. The explanation is that Algol B used to be the more massive star. It evolved, expanded, and transferred a large amount of its material to Algol A. Algol A gained mass. Algol B lost it. The star that now looks less massive is actually the one that started aging first. Mass transfer rewrote the evidence. This apparent contradiction became known as the Algol paradox, and resolving it helped establish how profoundly close binary interaction can alter stellar evolution. A star's present mass may not be the mass it was born with. Once binaries start exchanging material, simply looking at the 2 stars today does not necessarily tell you how the system began. Some interacting systems change brightness because of eclipses. Others vary because the stars themselves pulsate, because hot material moves around them, because an accretion disk becomes unstable, or because a thermonuclear eruption suddenly increases the amount of light escaping from the system. The general category of variable stars therefore includes many completely different physical situations. A changing brightness is an observation. The cause has to be discovered. One of the most dramatic groups is known as cataclysmic variables. A typical cataclysmic variable contains a white dwarf and an ordinary companion star in an extremely compact orbit. NASA describes many of these binaries as being comparable in overall scale to the Earth-Moon system, with orbital periods commonly measured in hours rather than years. The ordinary star loses matter, which is transferred toward the white dwarf. If the white dwarf's magnetic field is not strong enough to control the incoming gas directly, the transferred material usually does not fall straight down. It arrives with sideways motion. That angular momentum causes it to form an accretion disk. Gas travels around the white dwarf while gradually moving inward. As it loses gravitational energy, the material becomes hot. The disk can radiate strongly at visible and ultraviolet wavelengths, while regions close to the white dwarf can produce X-rays. The remarkable thing is that much of the luminosity in these systems may come not from nuclear fusion inside either star, but from matter falling through the white dwarf's gravitational field. Gravity becomes the power source. Some cataclysmic variables undergo sudden increases in brightness known as dwarf novae. Despite the name, a dwarf nova is not the same event as an ordinary nova. In a dwarf nova, an instability in the accretion disk causes stored material to move inward much more rapidly. The system brightens. Later, the disk returns to a quieter state and begins accumulating material again. A classical nova involves something more explosive. Hydrogen-rich material transferred from the companion collects directly on the white dwarf's surface. The white dwarf's immense gravity compresses that layer. Pressure and temperature increase until nuclear fusion begins explosively. A thermonuclear runaway occurs in the accumulated surface material. The system can brighten enormously. But the white dwarf itself survives. That last point is important. A nova is not normally the destruction of the star. After the eruption, mass transfer can continue. Another layer can accumulate. Eventually another eruption may happen. Most nova cycles take so long that humans observe only one eruption from a given system. A few recur frequently enough that historical observations catch them more than once. T Caroni Borealis, usually shortened to TCRB, is one of the best-known recurrent novae. The system contains a red giant and a white dwarf. Gas escaping the red giant is captured by the white dwarf and gradually accumulates until a thermonuclear eruption occurs. NASA records major eruptions in 1866 and 1946, with evidence for earlier events as well, which is why TCRB has become the standard example of a recurrent nova with a timescale of roughly decades rather than many thousands of years. This is a very different relationship from Algol. In Algol, a normal star transfers matter directly to another normal star. In TCRB, an evolved red giant supplies material to a compact stellar remnant. The gravitational potential near the white dwarf is much deeper, and the accreted hydrogen eventually undergoes explosive fusion on its surface. Another system pushes the same basic arrangement into an even more elaborate form. Our Aquarii is a symbiotic binary, consisting of a mirror-type red giant and a white dwarf. The red giant is highly variable in its own right. It expands and contracts, changing brightness as it pulsates. Meanwhile, the white dwarf captures material from its companion. NASA observations show that the system has produced repeated eruptions and large structures of ejected material, along with jets and X-ray emitting shocks. The stars move around one another on an orbit lasting about 44 years. The word symbiotic is used because the system combines two extremely different kinds of stars. One is a huge, cool red giant. The other is a tiny hot white dwarf. The red giant supplies matter. The white dwarf turns some of that matter into energetic radiation and outflows. It is an astronomical partnership in which one member continually loses material while the other creates explosions with it. Perhaps symbiotic sounds slightly more cooperative than the arrangement really is. The same basic idea becomes even more energetic when the compact object is a neutron star or black hole. These systems are called X-ray binaries because much of their observable energy emerges at X-ray wavelengths. There are several categories. High-mass X-ray binaries contain a neutron star or black hole paired with a massive ordinary star. Low-mass X-ray binaries contain a compact object paired with a lower-mass companion. The material can reach the compact object through Roche-Lobe overflow or through stellar winds. Either way, gas falling toward a neutron star or black hole releases enormous amounts of gravitational energy. The deeper the gravitational field, the more energy can be released before the material reaches the central object. Cygnus X1 remains one of the most famous examples. Its visible component is the massive blue supergiant HDE 226868. Its companion is a stellar mass black hole. The system completes an orbit in less than a week, and the massive star produces a strong stellar wind from which the black hole captures material. The resulting accretion environment produces intense X-rays. Cygnus X1 became historically important as one of the first objects for which the evidence for a stellar black hole became compelling. The black hole is not glowing. Matter outside the event horizon is. As gas falls inward, it becomes compressed and heated. Temperatures can reach millions of degrees. The inner accretion flow produces X-rays that ordinary stars cannot generate in such quantities. That lets astronomers locate a black hole without seeing the black hole itself. There are also black hole binaries that spend long periods in relatively faint states before suddenly becoming much brighter. V404 Cygni, also called GS 202 3+338, contains a black hole with a lower mass stellar companion. The two orbit every 6.5 days. Gas pulled from the star accumulates in an accretion disk around the black hole. For long periods, the system remains comparatively quiet. Then the disk can change state. Material suddenly moves inward at a much greater rate. The X-ray output rises dramatically. NASA observed such an eruption in 2015, the first major one since 1989. The black hole did not suddenly change mass or become a different object. The supply system changed. That distinction appears repeatedly in interacting binaries. The central compact object can remain broadly the same, while the behavior of the surrounding gas changes from quiet to violent. An accretion disk is not a smooth conveyor belt operating at one fixed rate. Material can accumulate. Magnetic fields can redirect it. Thermal instabilities can change how efficiently gas moves inward. Outbursts can begin and end. The system can therefore vary on timescales far shorter than the evolution of either star. Some accreting binaries do something even more striking. They produce jets. A small portion of the material moving toward the compact object can be redirected along the rotational axis and launched outward at enormous speed. When a stellar mass black hole or neutron star produces an accretion disk and relativistic jets, astronomers sometimes describe the system as a microquasar. The word comes from the similarity to quasars, which are powered by supermassive black holes in the centers of galaxies. A microquasar is the stellar scale version. The black hole may contain only several or tens of solar masses, rather than millions or billions, but the basic combination of accretion disk and jets is similar. These systems let astronomers study accretion physics on much shorter timescales. Changes that might take centuries in the environment of a supermassive black hole can occur over days or hours around a stellar mass object. A laboratory does not usually come with an event horizon, so astronomers take what they can get. Not every extraordinary interacting binary contains a compact remnant. Two ordinary massive stars can create spectacular high-energy behavior simply through their stellar winds. Eta Carinae is the outstanding example. The system contains two extremely massive stars in a highly eccentric 5.5-year orbit. Both stars drive powerful winds away from their surfaces. The primary's wind is dense. The companion's wind is faster. Where those winds collide, the gas is shocked to temperatures high enough to produce X-rays. The distance between the stars changes dramatically during their eccentric orbit, so the structure of the collision region changes as well. Eta Carinae also experienced its famous great eruption in the 19th century. It expelled several solar masses of material while somehow avoiding complete destruction. That material now forms the homunculus nebula surrounding the system. NASA estimates the combined mass of the binary, at well over 100 solar masses and continues using the system as a laboratory for understanding extreme stellar winds, mass loss, and the evolution of very massive stars. The stars have not yet become compact remnants, but they are living in a regime where mass loss and interaction will strongly influence what eventually happens. Each is massive enough to face an extreme final evolution. The binary nature of the system means their futures cannot be predicted simply by treating the stars independently. This is a recurring problem in stellar evolution. A textbook description might say that a star of a certain initial mass follows a particular path. That works reasonably well when the star remains isolated. Put the same star into a closed binary, and the companion can remove much of its envelope, add new material, spin it up, alter its core growth, or trigger a merger. Two stars with identical birth masses could therefore finish their lives very differently, because one had a close companion and the other did not. There are systems stranger still. AR Scorpii, shortened to ARSCO, contains a rapidly rotating magnetic white dwarf and a red dwarf companion. It became famous as the first known white dwarf pulsar. The white dwarf rotates roughly once every 2 minutes and produces sweeping beams of radiation that repeatedly strike the companion. The system's brightness pulses as that electromagnetic beam interacts with the red dwarf and surrounding material. This is unusual because pulsar behavior is normally associated with neutron stars. Neutron stars are tiny, strongly magnetized, rapidly rotating remnants. RSCO demonstrates that under the right conditions, a white dwarf can produce a broadly analogous lighthouse-like effect on a much larger scale. The object is less compact than a neutron star and rotates far more slowly than the fastest neutron star pulsars, but the general behavior is similar enough that the term white dwarf pulsar is useful. A star does not have to transfer large amounts of material continuously to create an exotic binary either. Sometimes the strangest part of the system is what seems not to be happening. Gaia BH3 is a good example. The system contains an ordinary low-mass star orbiting an unseen black hole of roughly 33 solar masses. It was identified from the visible star's astrometric motion, rather than from a bright X-ray accretion disk. The European Space Agency's Gaia measurements revealed the wobble, and ground-based observations confirmed the companion's unusually large mass. When announced in 2024, Gaia BH3 was the most massive stellar origin black hole known in the Milky Way. It is largely dormant. There is no brilliant accretion flow advertising its presence. This matters because it reminds astronomers that X-ray binaries are an observational subset of black hole binaries. We find active systems easily because they are bright. Quiet ones are harder. The galaxy could therefore contain many black holes in binaries that have gone unnoticed simply because their companions are not currently feeding them much material. A black hole does not need to consume its companion. If the orbit is wide enough, the pair can behave like an ordinary detached binary, except one member contributes almost no visible light. The visible star simply moves around something dark and massive. Astrometry turns that motion into evidence. There are also contact binaries in which both ordinary stars have expanded enough to touch or even share a common outer envelope. Ursae Majoris is the prototype of one major class. In these systems, two stars orbit so closely that both fill their Roche lobes. Material can move through a shared envelope. Their orbital periods are often less than a day. Because the stars continually eclipse one another and are distorted by their mutual gravity, the observed brightness changes in a smooth, repeating pattern. They are no longer conveniently spherical stars separated by large amounts of empty space. Each is stretched. The surfaces can come into contact. Energy can move through the shared material. Over time, some contact binaries may merge. A merger would replace two stars with one. That gives us a different way for a stellar system to change its classification. A multiple system can lose a member because the star is ejected. A binary can become a single object because the two stars merge. The resulting star may rotate unusually rapidly, or possess chemical and magnetic characteristics connected with the merger. In star clusters, some objects known as blue stragglers are thought to form through mass transfer or stellar mergers. They appear younger and more massive than surrounding stars because they have gained fresh material. A binary can therefore create a star that seems to have ignored the age of its neighbourhood. There are still more unusual possibilities. A neutron star can orbit a normal star. A white dwarf can orbit a neutron star. A black hole can orbit another black hole. A triple system can contain compact remnants, while a normal star circles farther away. A planet can orbit a white dwarf. Planets can orbit pulsars. A black hole binary can exist almost invisibly until precise astrometry gives it away. What makes these systems exotic is not that they use different laws of physics. They use the same ones. Gravity still governs the orbits. The angular momentum still has to be conserved. Gas still heats when compressed. Nuclear reactions still depend on temperature and density. Magnetic fields still act on charged particles. The unusual results come from combining ordinary physical rules under extreme conditions. Bring two stars closer together. Let one expand. Replace one with a white dwarf. Increase the magnetic field. Replace the white dwarf with a neutron star. Increase the mass again until a black hole forms. Tilt the orbit. Add a third star. Allow matter to transfer. The list of possible outcomes grows quickly. That is why describing stellar systems only by counting their stars eventually becomes insufficient. Two binaries can both contain two objects and have almost nothing else in common. One may consist of two quiet red dwarfs separated by hundreds of astronomical units. Another may contain a giant star losing gas into an accretion disk around a black hole. They are both binaries. Only one is producing enough X-rays to be detected across large parts of the galaxy. The difference comes from separation, mass, age, evolutionary state, and the ability of material to cross from one object to another. The same underlying system can move through several of those categories during its lifetime. A detached pair becomes semi-detached when one star fills its Roche lobe. Mass transfer begins. The donor loses its envelope. It becomes a white dwarf. The system becomes a white dwarf binary. Later, the second star evolves. Mass transfer may begin in the opposite direction. A nova phase could follow. Under suitable conditions, the two stars may merge. Every label describes only one period in a much longer history. The strange systems are therefore not separate from the quiet ones we started with. They are what ordinary stellar families can become. A protostellar binary forms inside a cloud. Two main sequence stars emerge. One evolves first. The orbit changes. Material moves. A compact remnant appears. The second star continues aging. Perhaps another remnant eventually forms. Perhaps the system survives. Perhaps it merges. Perhaps a supernova unbinds the pair. Perhaps a third star farther away changes the orbit over millions of years. Following a star system through time changes the way all of the examples we have visited fit together. A single star system, a binary, a triple, a planetary system, a protostellar disk, and an X-ray binary may sound like separate entries in a classification guide, but many are connected by evolution. The arrangement we observe is usually temporary. Temporary can still mean billions of years, which is comfortably long by human standards, but the system itself continues changing. The process begins before there are stars at all. Inside a molecular cloud, gravity acts on regions of cold gas and dust. A dense region collapses. If one concentration of matter dominates, the result may become a solitary protostar. If the collapsing material fragments into two or more centers, a binary or multiple system can form. Young stars are therefore born with much of their eventual architecture already taking shape around them. The statistics of stellar companions are closely connected to this formation process. Multiple systems are common, and their frequency generally increases with stellar mass. NASA's overview of multiple star systems notes the enormous variety, ranging from ordinary binaries to X-ray binaries, and systems containing many stellar members. Formation does not end when the central objects become recognizable stars. They remain surrounded for a time by gas and dust. Material continues falling inward. Disks develop. Jets remove angular momentum. In multiple systems, the gravity of nearby protostars can truncate or tilt disks. Some young stellar companions move closer together. Others move farther apart. Close encounters can eject one member completely. The arrangement that survives the first few million years may therefore differ from the arrangement that initially formed. This early dynamical sorting is especially important for systems containing 3 or more stars. Stable multiple systems usually end up hierarchical. A close binary might be orbited by a much more distant third star. 2 close binaries might orbit each other from farther away. If too many stars remain on similar orbital scales, repeated gravitational encounters can destabilize the arrangement. Eventually one star may be thrown out or the system may reorganize itself. Nature does not require that every star formed together remain together. A former stellar sibling can become an isolated star moving independently through the galaxy. This means a star we classify as solitary today may not have been born alone. The Sun probably formed in a group containing many other young stars. Most of those neighbours dispersed long ago. The Sun now travels through the Milky Way without a bound stellar companion, but its early environment was almost certainly more crowded. Other stars retain their birth partners. A binary can survive for billions of years if its orbit remains stable. A hierarchical triple can do the same. A wide companion may circle so slowly that one orbit takes thousands of years. The system can look practically unchanged over recorded history while still participating in long-term gravitational motion. At the same time, planets begin forming from the disks around those young stars. Dust grains grow, planetesimals appear. Planetary embryos collide. Gas giants must assemble quickly enough to collect hydrogen and helium before the gaseous disk disappears. Rocky planets can continue growing after much of that gas has gone. The final number of planets is not predetermined. Some systems produce tightly packed groups of worlds. Some contain wide giant planets. Some experience migration that sends planets close to their stars. Others lose planets through gravitational scattering. A planet can even be expelled into interstellar space. The mature planetary system is therefore a group of survivors. Our solar system demonstrates one particular outcome. 4 rocky planets remained in the inner region. 4 giant planets occupy wider orbits. Smaller bodies populate asteroid and comet reservoirs. The planets follow relatively low eccentricity paths compared with some exoplanets. Nothing about the laws of physics required that exact arrangement. Other systems began with different disk masses, different stellar masses, different migration histories, and different gravitational interactions. They ended differently. Binary stars add another layer. If 2 stars are widely separated, planets may form and orbit one star, while the distant companion provides only a relatively weak perturbation. If the stars are close, a large circumbinary disk may form around both. Planets can assemble there too. Kepler-16, Kepler-47, TOY 1338, and other systems have shown that planets can survive around binaries rather than needing one fixed central sun. A multiple star system can contain still more combinations. One planet might orbit the distant third star in a triple. Another system could contain a circumbinary planet, while 2 additional stars move much farther away. The basic requirement is not simplicity, it is long-term orbital stability. Once the system reaches the main sequence, stellar evolution slows dramatically. NASA describes the main sequence as the long phase in which a star maintains an approximate balance between gravity pulling inward and pressure supported by energy production in the core. For a star like the Sun, that phase lasts roughly 10 billion years. For a small red dwarf, it can last vastly longer. For a very massive star, it may last only millions of years. This difference means that 2 stars born at the same time can age at very different rates. Put them in the same binary and the contrast becomes obvious. The more massive member may become a giant while its lower mass companion is still comfortably on the main sequence. If the stars are far apart, the evolved star can follow something close to the path it would have taken alone. Its core changes, its outer layers expand. Eventually it loses mass. A sun-like star sheds its outer envelope and leaves behind a white dwarf. The system might then contain one normal star and one white dwarf. Nothing about the number of objects changed. The identity of one member did. Bring the stars closer and the future becomes different. When the evolving star expands, it can fill its Roche lobe. Gas flows toward the companion. The donor loses mass faster than an isolated star would. The companion gains material and may become more massive, hotter or faster rotating. The orbit reacts to the transfer. The entire evolutionary schedule changes. A star's companion therefore becomes part of its life cycle. This is why binary evolution cannot be reconstructed simply by taking two single-star models and placing them beside each other. Interaction creates pathways that isolated stars never experience. Algol gave us a clear example. The star that evolved first lost so much material that it is now the less massive member. Without knowing about mass transfer, the present system seems to violate the normal relationship between mass and stellar lifetime. Once interaction is included, the history makes sense. The same process can create white dwarf binaries. The first star evolves and leaves a white dwarf. Eventually the second star expands. Material may then flow toward the compact remnant. The system can become a cataclysmic variable or symbiotic star. Hydrogen accumulating on the white dwarf can ignite explosively and produce a nova. If the white dwarf remains intact, the cycle can repeat. Some binaries end up with two white dwarfs. Their future depends on separation. If they remain widely separated, they can spend immense periods cooling. If they orbit extremely close together, they can lose orbital energy through gravitational waves and gradually spiral inward. A merger may eventually occur. Certain white dwarf systems are relevant to Type 1a supernova research, although the precise pathways capable of producing these explosions remain an active area of astrophysics. The general lesson is simpler than the details. Stellar evolution creates new objects. Orbital evolution determines whether those objects remain separated, exchange matter, or merge. Massive stars proceed much faster. They exhaust successive nuclear fuels until the core can no longer generate enough pressure to resist collapse. A supernova may follow. NASA summarizes the basic remnant possibilities by noting that a sufficiently massive collapsed core can become a neutron star, while a more massive core can continue collapsing into a black hole. In a single star system, that event may leave one compact object moving through space. In a binary, the explosion has to happen while another star is nearby. That creates several possibilities. The system may remain bound. The sudden loss of mass can alter the orbit. The newborn neutron star may receive a kick from asymmetries in the explosion. If the kick and mass loss are large enough, the binary can break apart. The neutron star travels one way, the former companion travels another. A system that remained together for millions of years can be separated in seconds. If the binary survives, the new arrangement may contain a neutron star and an ordinary star. Later, material from the companion can fall toward the neutron star. An X-ray binary forms. The neutron star may spin faster as it accretes angular momentum. Some old neutron stars in binaries can be recycled into millisecond pulsars, rotating hundreds of times per second after being spun up by mass transfer. The companion may eventually become a white dwarf. The final result can be a millisecond pulsar paired with a white dwarf, an arrangement very different from the two ordinary stars that originally formed. For more massive systems, a black hole can replace the neutron star. If the binary remains bound, gas from the companion may form an accretion disk. Cygnus X1 shows the active version. Gaia BH3 demonstrates that a black hole binary can also remain comparatively dormant if little material reaches the black hole. The black hole is still present. The difference is how strongly the companion is feeding it. Gaia BH3's discovery through stellar motion, rather than bright X-rays, illustrated how astrometry can reveal this quieter population. Later, the second star can also collapse. The system might then contain 2 neutron stars, 2 black holes, or a neutron star and a black hole. If the orbit is tight enough, gravitational radiation removes orbital energy. The compact objects spiral closer together. Eventually they merge. These events produce gravitational waves strong enough to be detected across enormous distances. A binary that began inside an ordinary cloud of hydrogen can end as a collision between 2 objects from which matter has been compressed to extraordinary densities. The pathway is long, but every stage follows from the previous one. Multiple star systems create even more possibilities. Consider a hierarchical triple. 2 stars form the inner binary. A third circles farther away. The outer star can alter the eccentricity and orientation of the inner orbit over long periods. That can drive the inner stars closer together at certain points in their orbit. Tidal effects become stronger. Mass transfer may begin earlier than it otherwise would. The inner stars might merge. Later, the third star could interact with the merger product. A system containing 3 stars therefore has evolutionary possibilities unavailable to an isolated binary. 4-star and larger systems provide still more combinations, although stable examples usually preserve hierarchical structure. The outermost companions are also the easiest to lose. A passing star in a cluster can disturb a weakly bound outer orbit without greatly affecting a tight inner binary. Over billions of years, a system may gradually shed its widest members. A 6-star family could theoretically become a quadruple. A quadruple can become a triple. A triple can become a binary. A binary can merge and become 1 star. Counting the stars at one moment does not reveal the entire history. Planets have to survive these transformations as well. When a star loses mass, its gravitational hold on distant planets weakens. Their orbits can expand. When a star becomes a red giant, close planets may be engulfed. Farther planets may survive. Asteroid belts can be disturbed. Comets can move inward. Material can eventually fall onto the resulting white dwarf. This is why planetary debris around white dwarfs is so valuable. The host star has already passed through a major transformation, yet pieces of its former planetary system remain. WD 1856+534b showed that even a giant planet can remain associated with a white dwarf and later occupy a very tight orbit, presumably after substantial dynamical evolution. Pulsar planets demonstrate an even more unusual outcome. PSR B1257+12 has planets around a neutron star. Whether such planets survived some part of the original system, or formed later from processed material, they show that the death of a massive star does not automatically eliminate every possibility of planetary architecture. There is no simple rule stating that planets belong only around normal main sequence stars. A planetary system is an orbital arrangement. If suitable material exists and stable orbits are available, planets can appear in environments very different from the one around the Sun. That does not make every environment equally suitable for life. A planet near an active pulsar experiences radiation conditions unlike Earth. A world around a close binary experiences changing illumination. A planet orbiting a young flare-active red dwarf faces another set of challenges. A planet surviving a star's giant phase may have undergone intense heating, an orbital change. The architecture tells us what is possible dynamically. Habitability requires additional questions about atmosphere, temperature, radiation, geology, chemistry, and time. That distinction has been important throughout our survey. Calling something a star system type does not tell us whether it contains planets. Finding planets does not tell us whether any are rocky. Finding a rocky world does not tell us whether it has an atmosphere. Finding an atmosphere does not tell us whether conditions resemble Earth. Every additional conclusion requires evidence. The same caution applies when astronomers classify stars as single. A star with no detected companion may truly be solitary, or a companion may simply remain below current detection limits. A wide, faint star can be difficult to establish as gravitationally bound. A compact remnant may produce almost no visible light. A low-mass companion can hide in the glare of a larger star. The apparent categories improve as observations improve. Sirius looked like one star to human eyes until its companion was inferred and then observed. Polaris looked simpler until its additional members were measured. Castor became a 6-star system, not because new stars formed during the observations, but because astronomers uncovered layers that had always been there. Modern instruments extend that process. Spectroscopy reveals unseen companions through velocity shifts. Transit photometry finds planets through tiny dips in starlight. Radial velocity detects stellar wobble. Astrometry measures motion so small that they can expose dormant black holes. X-ray telescopes find accreting compact objects. Radio observations time pulsars with extraordinary precision. Infrared telescopes penetrate dusty star-forming clouds. Millimeter arrays image cold disks in which planets are still assembling. Gravitational wave detectors reveal compact binaries during their final moments. Different instruments are not looking at separate universes. They're examining different parts of the same system histories. A young stellar disk may be easiest to see at infrared and millimeter wavelengths. The mature star becomes obvious in visible light. An accreting neutron star may dominate in X-rays. A pulsar reveals itself in radio. A merging black hole binary can become most obvious through gravitational waves. The object changes. The best way to detect it changes too. That is one reason the universe contains such an apparently overwhelming number of star system categories. Astronomers classify what they can observe, and different stages emphasize different physics. Protostellar systems emphasize collapse and accretion. Main sequence systems emphasize stable stellar fusion and orbital architecture. Planetary systems emphasize formation, migration, and long-term dynamics. Interacting binaries emphasize mass transfer. Cataclysmic variables emphasize accretion onto white dwarfs. X-ray binaries emphasize accretion onto neutron stars and black holes. Pulsar binaries emphasize extreme rotation and precise orbital dynamics. Compact object mergers emphasize gravitational radiation. These are not isolated topics. They are connected stages and outcomes. Even our Sun belongs to that larger story. It is currently a solitary G-type main sequence star with a mature planetary system. That description will remain useful for billions of years. Eventually, the Sun's core will exhaust its central hydrogen. Its internal structure will change. It will expand into a red giant. The inner solar system will be altered dramatically. The Sun will lose substantial mass through its outer layers. Its surviving planets will respond by moving into wider orbits. The expelled gas will expose the hot stellar core. That core will become a white dwarf. At that point, the solar system will still exist in some sense, but almost every familiar feature near its center will have changed. The central object will be roughly Earth-sized. The planets that survive will orbit a stellar remnant. Smaller bodies may be destabilized. Some debris could eventually fall toward the white dwarf. If a distant astronomer were cataloguing the system then, they would place it in a different category from the one they would use today. The system did not vanish. It evolved. This is probably the most useful way to think about every star system we have visited. A solitary sun is not simply one permanent type. A binary is not one permanent type. A planetary system is not one finished arrangement. Each is a current state produced by formation, gravity, mass, chemistry, angular momentum, and time. Barnard's star shows us a small solitary red dwarf. Tau Ceti and Epsilon Eridani show other versions of single-star environments. Sirius gives us a normal star sharing an orbit with a white dwarf. Alpha Centauri expands the architecture into a triple. Castor shows how several binaries can be nested into one 6-star family. Kepler-16 places a planet around 2 suns. Kepler-47 demonstrates that several planets can share a circumbinary system. HL Tau and PDS-70 let us see disks and young planets, while the construction process is still underway. PSRB 1257 plus 12 puts planets around a pulsar. Cygnus X1 combines a massive star with a feeding black hole. Our Aquarii pairs a red giant with an eruptive white dwarf. AR Scorpii gives us a rapidly rotating magnetic white dwarf, behaving in a pulsar-like way. Eta Carinae shows what happens when two extremely massive stars force their stellar winds into violent collision. None of those systems requires a special new set of physical laws. The differences emerge from the values placed into the same laws. Change the mass, change the separation, change the age, change the number of stars, add planets, remove an envelope, allow mass transfer, collapse a core. The possible architecture changes. That is why asking what types of star systems exist eventually becomes a question about stellar history. We can sort them into useful groups, but the boundaries are not walls. A young binary can become an interacting binary. An interacting binary can become a white dwarf system. A massive binary can become an X-ray binary. An X-ray binary can eventually become a double compact object. A triple can lose a star and become a binary. A binary can merge into one object. A planetary system can survive several of those stages in altered form. The night sky hides all of these histories inside points of light. A star that looks solitary may have a planet. A bright point may actually contain 6 stars. An apparently ordinary star may be orbiting an invisible black hole. A faint white dwarf may be surrounded by the remains of planets that once circled a much larger star. A regular radio pulse may come from a neutron star with several planets of its own. Looking at the sky tells us where the light is coming from. Understanding the system tells us what is actually there. And if you're still awake after travelling from single suns through binaries, crowded stellar families, planetary systems, newborn stars, white dwarfs, pulsars, X-ray sources and black holes, you have covered an unusually large amount of astronomy for one evening. If you drifted in and out somewhere along the way, that works too. The systems we discussed have existed for millions or billions of years. They are unlikely to object if part of the explanation was missed. Before we finish, you might think once more about where you're listening from and what the night sky looks like there. Perhaps you can see only a few bright stars. Perhaps the sky is completely hidden by clouds or city lights. Perhaps you're already too comfortable to check. Any one of those visible points could represent something far more complicated than it appears. One might be solitary. Another may contain 2 stars. Another could be part of a triple or a much larger hierarchy. Some may have planets. Some may be young. Others may already contain compact remnants. From Earth they are reduced by distance to tiny lights. But the systems themselves contain stars moving around shared centres of mass, planets following long orbits, gas flowing between companions, and structures changing over timescales ranging from seconds to billions of years. If you found this long journey through stellar systems useful or relaxing, you can leave a like, subscribe to Science for Sleep, or share it with someone else who enjoys learning about the universe at a slower pace. For now, there is nothing else you need to keep track of. The Sun is continuing around the Milky Way. The planets are continuing around the Sun. Binary stars are continuing around their barycenters. Young disks are continuing to form planets. Old stars are continuing to change. Somewhere, a white dwarf is cooling. Somewhere else, a pulsar is rotating hundreds of times each second. And across the galaxy, star systems in every stage we have discussed are continuing their ordinary work under the same gravity that has guided them from the beginning. Sleep well, wherever you're listening from tonight,